Hey there, friend. It's Bruno again. By the way, you've really impressed me over the last couple of days, but hey, I have something to ask of you. I know it's the weekend, I know it's Friday, but we had a last-minute issue with one of our clients, and we need your help as soon as possible. You see, this client hosts one of the world's biggest dog competitions. And unfortunately, all their data has been wiped from the dog profiles. All these dogs are going to be competing this weekend and they need an online profile. And up until now, they've had humans manually create the dog profiles. But unfortunately, the competition is this weekend and their data, when it comes to what the dog's breeds are, is completely gone. And they have thousands of dogs and there's no way that a single person that they've hired can do this. So I need you to create a machine learning model that can detect the dog breed from a picture. And they need it ASAP in a couple hours. So you can do this, right? I told them that it's no problem, that we have a star machine learning expert here. So don't disappoint. All right, everybody. This is going to be a fun one. We're going to learn about neural networks. Up until now, we had some really good structured data in CSV forms. But now we get to images. No more Excel files with rows and columns that were easy to understand. How can we teach a computer to know what a dog is? What a dog breed is? This section is going to be a lot of fun. We're going to use tools like TensorFlow, transfer learning, and deep learning to dive into this topic. A topic that is becoming more and more important in the industry. And at the end of the day, we're going to build a machine learning model that is able to detect dog breeds. It's going to be a lot of fun, and it's going to be a fun project to add to your portfolio. So let's get started.
Welcome back, everyone. I am so excited for this next section. And of course, we're starting off with our 6-step machine learning modeling workflow. We've got our problem definition, data, evaluation, features, modeling, and experiments. Again, we're trying to just make this almost second nature with whatever machine learning modeling tasks we come across. If we've got some data, these are some steps that we can take to figure out insights from that data. Now, let's have a look at what tools we can use. And what's important is that in this section, we're going to have a look at TensorFlow. And now you might be wondering, okay, I see PyTorch here, I see scikit-learn, we've already had a look at scikit-learn, but what is TensorFlow? Well, that's what we're going to be diving into in this entire section. And we're kind of going to be teaching this one a little bit differently to how we've looked at the pandas, matplotlib, numpy, and scikit-learn section. Now, the reason being is because the book on TensorFlow and the book on deep learning and neural networks of what we're going to cover in this section is not as established yet as what scikit-learn is. So scikit-learn's been around for over 10 years, whereas TensorFlow, the version we're about to use, only came out a couple of months ago. So if you're watching this in 2020 or later on, really, the version of TensorFlow, TensorFlow 2.0, it might be a higher version by now, only came out at the end of 2019. So what we're doing in this section is we're using cutting edge stuff. And what's even more exciting is that we've got a new contender to our workspace environment, and that's Google Colab. Now the reason being is because we're going to need access to a GPU. We'll have a look at that in a second, but this is our workspace that we're going to be using for this section. Now, if you're not familiar with Google Colab, that's okay. We're going to go through it. It's very similar to a Jupyter notebook. Now, you might be thinking, what is TensorFlow? And that's a great question. Well, TensorFlow is a deep learning or numerical computing library. That's probably a better term for it. Now, it was first conceived by Google and they used it within their own, like it was an internal software library for all of their deep learning and machine learning needs. And it's actually now open source. So anyone can contribute to TensorFlow. The most recent update, the TensorFlow 2.0, it is packed full of updates that the community, the people like yourself and me who use TensorFlow have asked for, like, hey, this didn't really work. Can we make it a bit better? So older versions of TensorFlow, you don't have to worry about. What we're covering is the latest stuff here. TensorFlow is used to build deep learning and neural network models to gain insights out of unstructured data. Now, in the previous projects, we've dealt with data that's available in a data frame, so something that looks like an Excel spreadsheet. It has rows and columns. But deep learning is more suited to unstructured data, such as photos or audio waves or natural language text, unstructured data that doesn't really have any specific structure. And now TensorFlow allows us to build a deep learning model, kind of like a neural network, well, exactly like a neural network, to gain insights out of this unstructured data. And it also allows us to check and evaluate how our neural network, which is another form of machine learning model, is doing. Is it getting things right or is it getting things wrong? Now, why TensorFlow? Well, the most important thing is that we can write fast, deep learning code in Python. Now, what I mean by fast is that it's code able to run on a GPU. And if you're not sure what a GPU is, don't worry, we'll check that in a second. And TensorFlow is able to access many pre-built deep learning models. Now this is important. So like scikit-learn has a bunch of machine learning models built into it. We've already seen scikit-learn. TensorFlow also has the ability to access pre-built deep learning models. So we'll see how to do that in the upcoming project. It also enables you to do the whole stack. What do I mean by that? You can pre-process your data using TensorFlow. You can model it using TensorFlow. And you can also deploy a model that you build using TensorFlow. And we just spoke about this one. It was originally designed and used in-house by Google. Now it's open source. So people like you and me, we have access to exactly the same software that Google use in-house for their deep learning and machine learning workflows. Well, we spoke about a GPU. What actually is a GPU? Well, a GPU stands for Graphical Processing Unit. And the main thing you have to know for now is that it's a lot faster than a regular CPU is at doing numerical computing. So if you remember, if machine learning is finding patterns in data, aka turning data or information into numbers, finding patterns in those numbers, a GPU is what's going to help us to increase the speed of finding those patterns in those numbers. That's all we need to know. Now, if you remember way back in the Machine Learning 101 section, so this is why I've got throwback here, we looked at this slide, choosing a model. So we've got structured data here. You might choose a model and you might use one of these libraries on structured data like CatBoost, XGBoost, or Random Forest. We saw that in sklearn. Now we're going to start working with problem 2, unstructured data. So we've got photos or audio files here, and we've got model 2, which is more like a neural network. This is kind of what you'll see if you Google up neural network. And now these type of models, deep learning and transfer learning, work much better on unstructured data like we've just talked about. And so TensorFlow is what we can use to build deep learning models. And TensorFlow Hub is where we'll be going to use transfer learning, aka taking what one model knows and using it in another model. Now you might be asking, what is deep learning and what are neural networks? Well, I want you to think of it like this. Deep learning is just another form of machine learning. And neural networks, something like this, these are the type of machine learning algorithm that are usually referred to when we talk about deep learning. And so if we have this image of a dog and we're trying to identify, that's my dog, 7. How beautiful is she? And that's Bella in the background. But let's say we're trying to identify the breed of 7. A neural network might look at this image, convert it into numbers, and then go, okay, this little model here is going to remember what a leg looks like. And then this one here is going to remember what eyes look like. And then these ones, who knows what they're going to figure out. And then eventually we realize that this is an image of a Labrador, if our neural network is learning right. So this is what I want you to imagine a neural network as, is that the same process with all of our other machine learning models that we've looked at is you have an input, some kind of data, and then you have a machine learning model here, in our case, a neural network, and then you have some sort of output. Now, a neural network, you might be wondering, what are all these little nodes here? They're also called nodes. Well, these are small models within themselves. So what's going to happen here is that each of these small models is going to add up and figure out some kind of pattern in this data and then learn what that pattern relates to, aka the label. And so where does deep learning come from? If a neural network is just another type of machine learning model? Well, this is where the deep part comes from. When building a neural network, you might use multiple layers. So see here, we've got our original one, but then you might add more neural networks on top of your original neural network. And what this might do, and I say might because again, it's a lot of trial and error in this sort of model finding. That's why I said in the beginning, the book on deep learning is yet to be fully completed yet, because we're still working out the best way to lay out these neural networks. And so I've got here a few more boxes than what we had in the previous slide. And what this means is that as you add more layers here, these other nodes, these smaller models in the neural network, are going to start to be able to detect more and more features, and thus hopefully getting better at identifying the information in our unstructured data. Now, what kind of deep learning problems are there? Well, we've spoken about classification. We've also seen that in a heart disease project. But you might want to classify what kind of dog breeds are in an image, or whether an email is spam or not. In this case, this email is definitely not spam. Otherwise, there's a sequence-to-sequence problem, also known as sec-to-sec. And now, this is a kind of problem that happens with Siri or Google Home or something like that. It also happens with Google Translate. So it takes an audio wave, and it's going to translate that into some sort of text or command. And then finally, there's object detection, which is similar to image classification, but now you're trying to find out where a specific object is inside an image. So this is a kind of deep learning problem that a self-driving car might have to come into, or will come into if they're using cameras, right? It's trying to identify what objects are in an image. If a Tesla self-driving car has 8 cameras, it's always trying to pick up what objects are in its way. And I mean, there's many more deep learning problems out there, but this is 3 of the main ones that you're going to come across in your day-to-day life. Okay, and we mentioned transfer learning before. So what is transfer learning and why should we use it? Well, the main premise of transfer learning is taking what you know in one domain and applying it to another. So if you're training a machine learning model to pick up different dog breeds in images, and you're trying to train a machine learning model from scratch, that can be both expensive and time consuming. But if you've already got a machine learning model which has learned to identify other objects in images, the beautiful thing is you can use transfer learning, so taking what that machine learning model or neural network, taking those patterns that it's learned in another set of images, and then apply those patterns to your own problem. So this leads us to the question, why not take advantage of what's already out there? Why not take advantage of what another model already knows? That's what we'll be looking at doing in this project. And more specifically, what are we going to cover? Well, if you remember our scikit-learn workflow, our TensorFlow workflow is very similar. We've got to get data ready, but this time it's unstructured data rather than structured data. And this is the main premise here, and I will stress this until I go hoarse, is getting the data ready is essentially just turning our data into tensors, hence TensorFlow. And then once our data's in tensors, we pick a model to suit our problem. We're going to use TensorFlow Hub for this. And then we'll fit the model to the data, so aka get the model to find patterns in the data for us. And we'll learn how to make a prediction once our model has learned some patterns in our data. Then we'll evaluate our model to see if, hey, are these predictions, are they any good or not? We'll see how to improve through experimentation. And then we'll save and reload our trained model. Now, in a dot point form, we're going to go through an end-to-end multi-class classification workflow with TensorFlow. We'll see what that is in a second. We'll learn how to pre-process image data, so getting it into tensors. We'll learn how to choose a deep learning model. We'll learn how to fit it to the data, so learning the patterns. Then we'll learn how to make predictions with our deep learning model, so using the patterns that it's learned. Then we'll evaluate our model's predictions. We'll save and load our deep learning model. And then we'll use a trained model to make predictions on our own custom data. Oh, far out. This is a big section, but I'm excited. Now, what is the problem we're going to work on? It's a classification problem, and it's the Kaggle dog breed identification problem. So determine the breed of a dog in an image. And now this kind of problem is multi-class classification. So that means there is more than 2 options, but we'll have a look at this shortly. Now, where can you get help with all of this? Because we're learning concepts and code at the same time, all within a project. Do your best to follow along with your code. If in doubt, run the code. Remember, try it for yourself. Because we're using Google Colab, we'll see this in a second. Reading a doc string is a little bit different to a Jupyter notebook. You have to press Shift, Command, and Space to read it. If you're still stuck, don't be afraid to search for it. You'll come across Stack Overflow or the TensorFlow documentation. And then try again using what you found on Stack Overflow or TensorFlow's documentation. And then finally, if you're still stuck, never be afraid to ask. And of course, don't forget the Discord chat, which hopefully you're signed up to. Hopefully you're in there interacting with the other students. And now, without any further ado, let's go find those doggos. All right. So I just want to give you a quick overview of what we're going to be working through in this section. We're going to be using transfer learning in TensorFlow 2.0 to classify different dog breeds. And we're going to finish off with a full-blown end-to-end multi-class classification problem. An example project. And now I've chosen to do it this way because I think the best way to learn anything is to get hands-on. And now, of course, I don't expect you to remember everything off by heart that what we cover. What's more important is thinking about the principles of what we're going to go through. So if we come back to our workflow, is to remind ourselves if we're choosing a machine learning model or working on some kind of project, what kind of data do we have? Is it structured data? Well, then we should probably choose a model that's more suited to structured data. And we should probably remind ourselves that in machine learning, we have to get our structured data into numerical form. So these are the principles that we have to think about. And the same with unstructured data. Hey, if we're working with unstructured data like images, which is what we're going to be working with, we should probably use a deep learning or transfer learning model. All right, so like a neural network. And for that, we can use TensorFlow or transfer learning with TensorFlow Hub, which is what we're going to work on in this project. And again, our machine learning model, even if it's transfer learning, still can't look at images unless they're in the form of numbers. And in our case, since we're using TensorFlow, they have to be in tensors. So these are the principles I want you to start thinking about. And now, what are we going to do? As always, when we attack a new project, is to set up our project workspace. And now, traditionally, we've gone through this route. We've had our computer, we've downloaded and installed a Miniconda, we've started a new project in a project folder, we've put some data in an environment and a Jupyter notebook in there, and then we've got our coding libraries in our environment. And now, this is what's going to blow your mind, is Colab takes care of a lot of all of these steps for us, which is what this notebook is built in. Like, this is Google Colab, but it looks like a Jupyter notebook. Now, you might be asking, why didn't we just use Colab from the start? Well, Colab is great for working on projects like what we're about to work on, but there are some times where projects that you're working on can't be used with Colab. So that's where you go through this workflow. Now, we will require a GPU, a piece of computer hardware that's really fast at doing numerical computing. So that's why we're choosing to use Colab, because it's a Jupyter notebook running on one of Google's servers, which gives us access to a free GPU. And we'll see how to set that up in a moment. What are we actually working on? Let's have a quick look. We'll go to the Kaggle dog breed identification competition. So if we look at here, what we're going to do is determine the breed of a dog in an image. So because we're working with images, it's unstructured data. And so if we have a look at this, we go to data. So if we look at our data sources, what are we going to do? We're going to download labels CSV. We're going to download all of these. So we've got test. These are some images to test on, and then some images to train on. So if you go to kaggle.com/c/dog breed identification with hyphens in there, /data, that's where we're going to get our data from. So I'm going to log in here and download the data. So I've just logged in, and now I'm going to click download all. Beautiful. So this is going to take a couple of minutes. I'll pause the video until this download's done, and then we'll see what we can do with that in a moment. Wonderful. So my download has just finished from Kaggle. That took a couple of minutes on my internet speed. Now, what I'm showing you here, downloading the data, is just one option. You could always use the Kaggle API. Now, if you click on this little question mark here, again, the website's just here. This will give you some documentation about how to use the Kaggle API, which works in Google Colab. However, I've chosen to do it this way because if you want to work on your own custom data set, like one that wasn't hosted on Kaggle, this is one way to do it. There is actually, if we search up Google Colab IO, there is an example notebook. Here we go. I'll link this in the resources section. There is an example notebook in Google Colab. And the beautiful thing about Google Colab examples, so if you Google something and go Colab, I just Googled IO, is that these are all runnable Jupyter notebooks immediately. So this is going to give us a little bit of an idea about how to load external data, because remember, machine learning is all about getting our data ready. How can we load external data from local drives, sheets, and cloud storage into our Colab notebook? So how can we get this zip folder into our Colab notebook? This demo will show us, but I'm just going to show you the way that we're going to do it. And so we're going to go to colab.research.google.com. You will need a Google account. And so we are going to just start a new Python 3 notebook. And now, again, if you want some examples, there's a whole heap here. Feel free to search them up and check them out in your own time. But we're going to start a new Python 3 notebook. Beautiful. Look at that. This is kind of similar to what we've been working with Jupyter. Now, there are a few different commands and a few different things that are slightly different to our Jupyter notebook. But the main premise of what we were doing in Jupyter, it comes over to Colab. So if we want to write code, we can go import pandas as PD, shift and enter. Or we could go numpy, import numpy as NP, shift and enter. And if we wanted to add a text cell with some markdown, we can go, this is a Colab notebook, shift and enter. See? Just like a Jupyter notebook. Now, there are a few subtle differences, and we're going to see that in the next video. So in this one, we just downloaded the data. I've got that in my downloads folder now. We've seen an example Google Colab notebook of how we can load external data into our Google Colab notebooks. And we've seen what we're working towards, this end-to-end. I've called this project Dog Vision. I like that name because we're trying to identify different dog breeds in images. But without spoiling too much, start up your own Colab notebook in Google Colab, and I'll see you in the next video. Alrighty, now we've got a Google Colab notebook running. Let's get it set up for our project. Now, if you read through the external data, Google Colab, the notebooks, io.ipynb, that's a little tidbit too. So even though we're working in Google's program here, Google Colab, it's still running the same extension as our Jupyter notebooks, so ipynb. So we can go here, download ipynb. So if we did that, it would download this notebook here from Colab in the format of a Jupyter notebook that we could load in Jupyter, the workspace we've been using previously. So that's just a little tidbit to know. Now, if you read through that, you would find that there's one way if we wanted to upload files to Google Colab, we could go to this little file tab here and click upload. Now, that is definitely one way to do it. However, what you might find is that when your Google Colab runtime disconnects, and you might be wondering, Daniel, what's runtime? Well, that's over here. So you see this little tick? And if we read that, connected to Python 3 Google Compute Engine backend. So this is where we can access a GPU, right? This Colab notebook is actually not running on our computer anymore. It's running on Google's servers. So that's where you can see there, connected to Python 3 Google Compute Engine backend. So this notebook is being powered by one of Google's computers in their warehouse. And if we uploaded data through here, if our runtime disconnected, like what you'll see, a message like this, it's going to remove all of the data from here because we can't just keep storing data on Google's machines. Otherwise, they'd just get overflowed and we'd lose data, and some data you might have might be private, so it shouldn't be stored on Google's machine anyway. Now, if you're wondering, okay, Daniel, a lot of this sounds confusing, runtimes, all this sort of stuff, but it's important to know because if you were to upload your files here and then the runtime disconnects, say Google's machine just shuts down on you, you'd lose everything that you're working on, which is not an ideal scenario. Now, if you're wondering how long does a session last, well, this is, again, something that's really hard to answer because I've had times where I'm sitting here coding away. That wasn't code, but you could pretend I was coding. And the runtime, I get a message like this, runtime disconnected. So I've written here, a Colab connection will sometimes drop out. It's hard to tell when. If it does, you'll need to reconnect and potentially rerun all of your cells. So if you see this message, right, it won't always come up, so I can't guarantee that it comes up during the videos. Press reconnect, and you might have to rerun your cells like this. And if you're wondering about more information about how a Colab workspace runs, I'll leave this in the resources as well. So if we go Google Colab FAQ. So these are some frequently asked questions. A great little resource here. This is your homework before the next video is to read through this. So what is Collaboratory? Is it free to use? Yes, it is free. What are the limitations? So this is what we're looking at. Colab resources are not guaranteed and are not unlimited. The usage limits sometimes fluctuate. So that's why we might randomly see one of these runtimes disconnected. And you might also see one of these messages, but we haven't connected Google Drive to Colab yet, so this won't appear just yet. We're still in the process of getting our workspace set up. So as quick as Colab is to get started compared to Jupyter, there are still a couple of little issues because providing a free service like this is what Google's doing is no easy thing to do. So we'll see where this might come up in the next video. But in the meantime, I want you to read through the Collaboratory frequently asked questions. I'll leave that in the resources section. And just make sure that you've got a little green tick here. And if you don't, this will change to connect. And I want you to click on that and see what it says. Hopefully you've gone through the frequently asked questions on Google Collaboratory, because I know when I first started using Google Colab, I ran into a bunch of things that would have definitely been solved if I just read through there. So don't make the same mistake that I made and not just quickly read through. It's like when you have an opportunity to read documentation or just fumble around coding for hours. I mean, one would argue that fumbling around coding for hours helps you learn more, but there are some things that you can just quickly get an answer to by just spending 5 to 10 minutes having a little read. Okay. Now, how do we get this little zip file that we've downloaded from Kaggle through here? How do we get this into our Collaboratory notebook? We have no project if we have no data. Let's do that in this video. What I might do is give this a little name. So I'm going to call this Dog Vision because I love that name. It sounds cool. And I'm going to delete these cells. Wonderful. And then what I'm going to do is I'm going to click this one, Mount Drive. And I'm not going to talk about it. I'm going to do it and then see what happens. Mount Drive. So what does this do? Permit this notebook to access your Google Drive files. Okay. So connecting to Google Drive will permit code executed in this notebook to modify files in your Google Drive. So if we were to read through this, Google Colab, the I/O notebook, how do we get it? This is the one we're going to follow through with. Mounting our Google Drive. So Google Drive is what you get when you have a Google account, is like a cloud storage for all of your information. And so we're going to connect this to our Google Drive. We're going to upload this zip file to our Google Drive and then work with the data in this Collaboratory notebook whilst it lives in our Google Drive. So just exactly like we were working with Jupyter, and except it was accessing data on our local computer. Now all of our data and code is going to live in Google Drive rather than our own computer. So let's connect to Google Drive. It's going to ask me to sign in, choose my account. This is my account here. I'm I'm going to get a little progress bar here. Mounting Google Drive. Beautiful. So if we go here, now I've got access to all of the files in my drive. Wonderful. So there we got Colab notebooks. This is where all of our Colab notebooks are going to be stored. So you can see here, I've got a couple of versions of this project because while I was building out the whole project, I was going through a few iterations, and we're at the final one now. That's what we're going to be replicating. We're going to create a new folder in Drive, so it turns out we can. Remember, if in doubt, run the code. And so we're going to rename this Dog Vision. Beautiful. May take a little while to update. So if we go into Dog Vision, there's going to be nothing in there, of course, because we just created a new file. I'm using Google Chrome, so my download will be here. If yours isn't, go to your downloads folder. You can probably grab it from here. And then to get this zip file that we downloaded from Kaggle into our Google Drive and subsequently eventually into our Google Colab notebook, we can drag it into here. Oops. What's this? Reminder, uploaded files will get deleted when this runtime is recycled. Ah. Okay. So if we go more info, where's this take us? Back to the frequently asked questions. Ah. Now you can see where I got tricked, right? Because my instincts were to drag and drop files into here. Not the right way to do it. So the best way to do it, right click here, upload. And so let's go upload. And we're going to go into our downloads folder, click dog read identification.zip, open. Now this is going to upload it to the correct file. So if we look there, dog read identification.zip. You also get this one, which is actually uploading it to this runtime here. So if we did it this way, with this little progress bar, it's going to delete all of our data if our runtime disconnects. So remember, the correct way to upload if we're using Google Drive, if we've mounted our drive, is to go here, right-click upload, or you could also do it through drive.google.com. So if I go into, I've got Dog Vision now. So we can see here, this is going to be uploading for a little while because it is 13 megabytes is uploaded to Google Cloud so far. But if I come back to my local computer, it's actually 724 megabytes. So we're going to have to wait a little while until our data is in Drive. So I'll let you do that. Remember, you can also upload it just by dragging it into Google Drive. Make sure you're at drive.google.com. I'm not going to drag mine into there because it's already uploading through Colab. So once this is fully uploaded, we'll come back, and because it's a zip file, we'll need to unzip it so we can access the information that's in there. Whew. So a few steps there. All I did was click Mount Drive. It's now Unmount Drive because I've done that. I created a new folder in my Google Drive called Dog Vision. That's where we're going to be working on this project. And then I made sure to right-click on Dog Vision and click Upload, where I uploaded the dog read identification.zip file that we downloaded from Kaggle. So go through those steps, check out your Google Drive, make sure that it's uploaded all of the megabytes. Don't get caught out like I did trying to access this zip file before it's all uploaded to Google Drive. So once that reaches 724, may take a while, so this is probably now a good time to go have a break, have a cup of coffee, go for a walk or something like that, and come back when the data's uploaded and ready to go. So it looks like my file is completely uploaded because this number hasn't gone up in a little while. And now you may notice a little discrepancy between what the file appears to be in size here on my local machine, 724.5 and 691. But this has 724, 495,926 bytes, which equates to that. So there may be a little bit of a a discrepancy in terms of how Google Drive stores files compared to locally and how it represents size, but it looks like all of the files have uploaded, which is what we're after. So now we've got our zip file in our dog vision folder on our Google Drive. The next step is to unzip it, much like we could locally. So if I just double click here, it's going to expand dog breed identification.zip. So we'll have a look at what's inside. Beautiful. So this is what we're after. Train, test, sample submission, labels.csv. And this is what Kaggle says it's going to give us if we were to download the zip. Labels, sample submission, test, and train. And in labels, we have 10,222 unique values. Okay, wonderful. So these are the kind of things that we can test to make sure that even if we see a little discrepancy here, we can test once we've got our data in our notebook. Hey, does this line up with Kaggle? So that's what we'll have a look at now. So how do we unzip this in Google Drive? Now there may be a way we could do it from here, but we're going to see how to do it with code. So let's go unzip. And now remember, these cells here are just like in Jupyter. If we want to run something that's like on the command line, we can use the bang symbol here or the exclamation mark. So this is going to go unzip and then we give it a file. We need the file path here. I believe you might be able to go copy path. Oh, if you can, that's going to save us some time. Beautiful. We could do that, or we could just type it out for practice. So you actually don't need content, little tidbit there. So we can go here. Let's see how we type it out. Drive, because we got drive here. Drive, my drive, don't forget the space. My drive. Yours might be named a little bit different to mine, but this is just what mine looks like. Our target file is this, so your target file will be the same as mine. My drive, and then the project folder is dog vision. So we need to go dog vision, dog space vision, and then dog breed identification .zip. Is that spelt right? I believe so. And then we're going to pass it the D tag for destination. And then we want to put it in drive, just the exact same folder. Drive, my drive, dog vision. We just want to unzip it where it lives. I believe that should be enough. Wonderful. Let's run this cell. We can hit Shift and Enter. Or we could hit that little play button, this little play button here. And now we're going to get a big output of messages here because it has to go through and unzip 10,000 files into Dog Vision. Now, it may take a little while for this folder to update over here, but we can be sure that it's running by having a look at all this. So see, these are all test images. Now, again, this might take a little while. So while this code is running, I'm going to stop this video here and we'll come back in the next one once we've unzipped all of our data in the Dog Vision file, and then we'll have our data ready to be used for our project. There we go. We've got some updates. So this may take a few minutes to run. Make sure it's fully run before we go into the next segment, because otherwise, if it's not fully run, you'll come into the same mistake I made when trying to work with your data before it had been unzipped. And so you end up working with less files than what Kaggle says there is. And that causes whole bunches of errors down the track. So we'll let this run. It may take a few minutes, but I'll see you in the next video once this is completed, and we'll go through what it's unzipped. Wonderful. So that took about 5 minutes on my machine. Now, again, this will really depend how long. Look how many files there are. Far out. Close to 10,000 images in the test file and over 10,000 images in the training file. But if we have a look here, we started with this zip file, then we ran this command to unzip it, and now we've got sample submission CSV, label CSV, train, and test. And if we come back to our local machine, we can see we've got the same folders here. So it's as if we've just unzipped the file on our local machine, but we've done it in Google Drive. And now we can access these files in Colab. If we come back to Kaggle, we've got the exact same data sources here. Now, again, you could have done this with the Kaggle API, but I'm just showing you what if you didn't have a data set that was on Kaggle? This is just one way to get data into your Google Colab notebook from Google Drive. And if we come back over into our Google Drive, we go back to Dog Vision, have a look at the test folder, we can see what some of the images look like. But again, we're not really worried about looking at them in Google Drive. We're more worried about looking at them in Google Colab. We've gone through the steps that we needed to in our setting up our project folder, so getting our data ready. Let's see how we can interact with code. So now that our data's in our Colab notebook, let's finish setting it up and getting it ready for this project. Now we've got our data ready in our Colab notebook and in Google Drive. Let's clean up our notebook and get it more set up towards our steps that we take in a new project system. So what we've done, we've got Colab, we've created a new project folder, we've got our data in there. We actually don't really need to create an environment of tools because Colab already has a lot of them installed for us. Let's try to import some anyway. Because what are we doing? We're working with TensorFlow. And this is what we're doing. We're getting our data into tensors. Yes, we're going to use TensorFlow for that. And we're going to use TensorFlow Hub to pick a model. How about we get our notebook set up for those two in this video? That sounds like a good idea. If we go back to Colab, what we can do, we can pretty up this. Because we don't need to run this zip command, we could delete the cell or we'll just comment it out for now. So we'll run that. We can close this down, get rid of that, really just tidying up our notebook, getting it ready. What we might do is add a text cell. And we're going to move that up there. And I'm going to put the title in this. So we'll go, I'm going to put a little emoji because it's nice and fun. So we'll go end to end multi-class dog breed classification. And go, this notebook builds an end to end multi-class image classifier using TensorFlow 2.0 and TensorFlow Hub. Wonderful. And so let's get our little headings up in here. So problem, data, evaluation, and then features. So this is again from our 6-step workflow. So we might put in here 1, 2, 3, 4. So problem is identifying the breed of a dog given an image of a dog. Now, there's 120 different dogs. I don't know if you can identify that many breeds, but I certainly can't. So imagine, this happened to me the other day, right? I was sitting at the cafe and a dog walks past and I can't even remember the breed name, but someone next to me said, oh, let's make one up. That's an Australian Terrier. Well, that makes sense because I'm Australian. That's an Australian Terrier. I'm like, wow, how did they know that? And then I realized I only know about 3 dog breeds, like German Shepherd, Labrador, and Beagle. I only got that one because I'm reading that. And so this is what dog vision could be used for. If we were trying to build something that could identify, if I was sitting at that cafe and took a photo of that dog, could my machine learning model, the one that we're going to build, tell me what breed it was? So that's our problem. It's like, that's our statement. When I'm sitting at the cafe and I take a photo of a dog, I want to know what breed of dog it is. That's our problem. We're putting it in real life terms, right? And now where's our data? We can get our data. We'll just put a link here from Kaggle. So the data we're using is from Kaggle's dog breed identification competition. Then we'll put a link here. Evaluation. What is our evaluation? So in our head, I want you to think about this before we even look at Kaggle. Because we're working in classification, what is a good evaluation metric for how well our dog vision is performing? Well, one of the default metrics for classification is accuracy, right? So if we could get it pretty accurate at predicting what dog is in a photo, that's a pretty good metric. But let's see what Kaggle says. So if we go to overview, evaluation. Submissions are evaluated on a multi-class log loss. What is that? Between the predicted probability and the observed target. Well, there's a link here, so let's click that. Oh, wow. Okay. Well, these are things you're going to have to deal with in real life, right? You're never always going to go down the right path. 404, and I like how they've done that with some data there. Well, multi-class log loss. Let's have a look at the example. We've got ID, which is this long string. We've got a dog breed here, Affenpinscher. Don't mock me for not being able to pronounce that. Afghan Hound, that's an easier one to pronounce. And 0.0083, 0.0. These look like output prediction probabilities of a model, and which they are. So here we go. Oh, if I could just read this, remember, if in doubt, read the documentation. Or run the code, either or. For each image in the test set, you must predict a probability for each of the different breeds. The file should contain a header and have the following format. Okay, so this is what we're working towards. If we wanted to make a submission, this competition is closed. See, it's a playground prediction competition. But we can still make a submission. Let's work towards that. And that's the file type we need. All right. So if we go back, where were we? Dog vision, evaluation. The evaluation is a file with prediction probabilities for each dog breed of each test image. And then we go here. We'll copy that. Put it into dog vision, so if we ever needed to come back, we can. And then some features of the data. Well, we know that they're images, so they're unstructured. But let's have a look at our data. We have 120 different breeds of dogs, so there's 120 different classes. I'm going to copy that. Some information about the data. We're dealing with images. This is the way I want you to start thinking about different projects, right? This doesn't have to be like formal. By the time you've had some practice with problems, you won't need to write this out, but this is a good habit to have, is that you're communicating your work, not just to others. Like if we were to share this notebook, that's a really cool thing about Colab as well. You can share them, but it's communicating it to yourself so you know what you're working towards. Unstructured data. So unstructured data is just anything that isn't in a data frame, so no rows and columns. We're dealing with images, unstructured data, so it's probably best we use deep learning / transfer learning, which is what this project is all about. What else is there about the data? There are 120 breeds of dogs, and because it's multi-class classification, this means there are 120 different classes. Now, if there were only 2 dog breeds, it would be binary classification. If you remember our project on heart disease, that was binary classification. So whether someone has heart disease or not. So if we come back, labels CSV. So 10,222 unique values. Okay. So that means I'm guessing there is 10,222 different images. Okay, so 10,000 training images. You know what we might be able to do is if we have this locally, is go Command I on that. Boom, look at that. Thank you, Mac OS. You might be able to do this in Windows, I'm not entirely sure. We've got 10,358 items. And let's see if my theory was correct. 10,223 in train. I wonder what that is, where the little discrepancy is from there. That's all right, we'll figure it out. We're not worried about that now. We're cooks, not chemists. There are around 10,000 plus images in the training set. There are around 10,000 plus images in the test set. These images have labels. These images have no labels, because we'll want to predict them. Wonderful. So this is us setting up our project space. And now I know at the beginning we kind of said we're going to import TensorFlow, but what's more important is getting our heads around what problem we're actually trying to solve before we start bringing in our tooling. So if we go here, unzip the uploaded data into Google Drive. Wonderful. So I'm going to delete this cell. What should we do now? We might as well import TensorFlow because that's what we're working with, right? We come back to our keynote. This is our workflow. We're working with unstructured data. So get our data ready. We've got it uploaded into Google Drive, correct. Get it into Tensors. We're going to use TensorFlow for that. And TensorFlow Hub. So that's what we might as well try and do. We might as well try and import TensorFlow and TensorFlow Hub. How might we do that? So you could do this. If you have any question, you go how to import TensorFlow. I already know, so I'm just going to show you, but that's just an example. Actually, we're working in Colab, so it's better to be a bit more specific in Google Colab. That's just what I would Google. Oh, look at that. A great video. Oh, that's the old TensorFlow logo. So if you see that logo, that's the old TensorFlow logo. We're dealing with TensorFlow 2.0. So we want to import TensorFlow into Colab. So let's put a little heading here. Get our workspace ready. Now the beautiful thing about Colab as well, little tidbit, is that once you do headings in their own cells, you get this little section over here. So we could go right to the top or we could go back to this section. So that's what we're going to do throughout, is just navigate through this. So we want to get our workspace ready. The import, nice and simple. Import TensorFlow as TF. If you ever see TF, just like NumPy is NP, Pandas is PD, TF is short for TensorFlow. We want to go print TF version. And now this is going to tell us what version, because we're after TensorFlow 2. Oh, and look at this, Google Colab. Autocomplete on tap. Thank you, but we're going to try and avoid using autocomplete because we want to practice writing the code ourselves. Let's see what happens. Oh, red text. Too many underscores. That's the first mistake. Oh, we missed out on that red text. That's all right. I'm going to show you. I'm going to restart my runtime. Remember, if you ever see what I just did, if you ever see this come up, you might have to go to runtime, restart runtime. But I'm going to just show you. We don't have to worry about that cell because we've already unzipped our files. Show you this red text. Hopefully it comes up again. Boom. That's what we were after. So the default version of TensorFlow in Colab will soon switch to TensorFlow 2.x. That's what we want, the new version of TensorFlow. See, you might, if you're watching this video in the future, you might already have TensorFlow 2.x or 2. Whatever. We need 2 something. Because I'm running this, it hasn't switched over yet in Colab. So I'm using TF 1.15, which is not what we want. We want the 2.0 version. I'll see you in the next video. I'll show you a little trick if you don't have TensorFlow 2.0 yet. If you do, keep going, skip the next video. But if you don't, watch the next video. Now, this video is if this doesn't return TensorFlow 2 something. So this project is based off TensorFlow 2.0 and above. So we need to import that. If you run this cell and your TensorFlow version is over 2 something, you can skip this video and continue on to the next one. This is if your TensorFlow version is like mine and under 2.0. Let's see how we'll do it. So we want to go import. There's a little trick in Colab to get it without running through these upgrade steps. Don't worry about this upgrade steps. I'll just show you the code to do it. So try. Now we want to run a TensorFlow magic. Now the important thing to note is that this magic function, remember a magic function in Jupyter is one that begins with a percentage sign. This will only work running this in Colab. It won't work if you run this magic function in Jupyter. That's something to note. You'll have to install TensorFlow 2 manually if you're using Jupyter. So that's probably where you'd go to this upgrade link. But if you're using Colab, just run this cell. So that's just that comment telling you that this magic function only exists in Colab. So TensorFlow, we want version 2.x. So this is just saying, hey, load TensorFlow 2.x, except, exception, pass. Now let's see what happens when we run this. TensorFlow is already loaded. Please restart runtime to change versions. Okay. So this is where we'll have to go up into runtime and restart our runtime. Remember, this is just like in a Jupyter Notebook if you are restarting the kernel or something like that. It just means that it's just going to reset all the variables stored on Google's machine and we can reload them in a fresh manner. Wonderful. So if we ran this, we'd re-import the old version of TensorFlow. But if we run this, we should get TensorFlow 2.x. Boom, TensorFlow 2.x selected, and now let's check it out just to make sure. Print tf version. We go tf dot underscore underscore version underscore underscore. Oh, I think I've got 3 there. TF is not defined. What are we doing here? We need to re-import TensorFlow. Of course. Silly sausage, Daniel. So if we go import TensorFlow as TF, autocomplete, thank you, Google. And is it going to be 2.x? Please let it be 2.x. Wonderful. 2.1.0. We're already at version 2.1. Things move fast. Okay, so we're going to wrap up this video nice and short. That's just how to load in TensorFlow 2.1.0, which is what we use in this project. If you get this message by running this cell. If you ran this cell previously and you get TensorFlow version 2 point something, ignore this code here. So I'm just going to comment this out for me for now, so I don't accidentally run it. Beautiful. I'll see you in the next video. Awesome. So now, if you print out this little line here, it should print out something like this. TF version, I'm using 2.1.0, but if yours is 2 point something above, that should be fine. Unless TensorFlow have broken all the code that we're working on here, which is unlikely. But I should have put up in here, getting our workspace ready, I should have put up what we're actually going to do. So we need to import TensorFlow 2.x. We've done that. We can put a little check mark beside that. I wonder if we can. I'm going to put an emoji next to that. There we go. Green tick. Wonderful. We need to import TensorFlow Hub. And we also need to make sure we're using a GPU. Remember in the introductory lecture we said we're going to need a GPU because when we're working with unstructured data, oftentimes the patterns are a lot more vast, and running a neural network, a special kind of machine learning model, takes a lot more compute power than what a traditional machine learning model, like something like a random forest we've ran in the past has. Or at least in our case, because we're dealing with a lot more data this time. We've got 10,000 plus images, nearly a gigabyte worth of data. So whereas our previous CSVs were only a couple of megabytes or kilobytes, even if less than that. So we've imported TensorFlow 2.x. Now we need to figure out how to import TensorFlow Hub, okay, and make sure we're using a GPU. And now if we come back, the reason why we need TensorFlow Hub is because this is where we're going to pick our model from. And the reason why we need TensorFlow is, of course, to build this whole pipeline and to get our data into tensors. So we're still getting our workspace ready. Let's import TensorFlow Hub. So we'll put here, I'll write a little comment, import necessary tools. We could import a few more that we'll use, but we might import them as we go. But I just want to make these two known right at the top because these are the main ones of this entire project. So import TensorFlow Hub. It's already installed in Colab, which is beautiful. Another great reason for using Colab. As Hub, that's the traditional TensorFlow Hub way of importing it. Then we can also go print TF Hub version, same way. We'll go hub dot underscore underscore version underscore underscore. Wonderful. And then we're going to write a little line here now that we've imported TensorFlow, which will help us check if there's a GPU available. Because TensorFlow, what it does is it allows us to write Python code which gets executed on a GPU. So TensorFlow, underneath all the TensorFlow code that we write, calls another library, which allows our code to be run on a GPU, in turn, make really fast numerical calculations. So let's go here, check for GPU availability. And now another reason why we're using Colab is because Google kindly provide free GPU access to us. So my laptop, if I was to try run this project on my laptop, it would probably burn out before it could even figure it out. It could run for days on end. But what we'll see as we eventually get to it, because we're going to be using a GPU, it runs a lot faster. And even then, it's going to take half an hour or so. We're getting ahead of ourselves, Daniel. Come on, let's just check if the GPU is available. So I'll show you a little bit of code you can use. It's TensorFlow based to see if a GPU is available. Now I'm going to write out a little success message because I love seeing that we have access to a GPU. And you should too, to be honest, because this is what's caused the deep learning revolution, is the access to GPUs. Now, what is this little function doing here? Well, I want you to try and imagine, what is it doing? We're accessing TensorFlow, TensorFlow's configuration, and it's going to list the physical devices. And that literally means what you might think it means. What physical devices are powering this Python 3 Google Compute Engine backend? So we can see RAM there, gigabytes, 1.11, and we got disk. But what else is there? We are most concerned with the GPU. So we're just going to pass it the GPU string. This is people who have written TensorFlow have had this problem before, and they've gone, let's just make this easy to check if we've got a GPU. Else not available. Unhappy face. So we run this. Let's see what happens. Oh, well, we do have TensorFlow Hub. That's beautiful. And we go GPU not available. And you might be asking, what is TensorFlow Hub? Well, this is where I'd encourage you to do your own research. I'm going to go through it in a moment, but you can go, what is TensorFlow Hub? Search that up. Have a quick read if you want to check it out, but don't worry about that for now. What we're focused on is getting a GPU available. All right, how do we do that? Well, let's figure it out. So if we go to runtime, we can go to change runtime type. Now, again, this is our runtime here. This is a lot of things that look a bit complicated, so connect to a hosted runtime. Okay, let's go runtime, change runtime type. This is how we get access to a GPU. We've got runtime type, Python 3. I'm recording this in post 2020, so Python 2 is no longer supported, so always Python 3. That means Python 2 just won't be getting any more updates. It'll probably still run for a while. Hardware accelerator. Let's click this. What does this mean? Let's zoom in. What type of GPUs are available in Colab? Beautiful. So this is necessary for Colab. The GPUs available in Colab often include NVIDIA K80s, T4s, P4s, and P100s. Again, if you're curious what these are, Google NVIDIA K80, NVIDIA T4, NVIDIA P4, NVIDIA P100. Long story short is that these are different types of NVIDIA GPUs. NVIDIA is a GPU maker, like Intel is a CPU maker, and these are just different models of chips. So let's go in here. We're going to choose a GPU. You could also choose TPU, but we're focused on GPU for now. TPU requires a little bit more setup with the code, but that could be, again, something that you could look up yourself, how to use a TPU in Colab. That's a bit of a rabbit hole you can get down. But let's go GPU. Click Save. Again, to do that, runtime, change runtime type, GPU, and you'll see, we've remounted Google Drive, and this is changing. Look at that. Oh yeah, connected to Python 3 Google Compute Engine backend GPU. Wonderful. So, what we have to do now is, because we've just restarted our runtime, we're going to have to, if you've already got access to TensorFlow 2.0, like if the output of this cell is TensorFlow 2.0, you can just rerun this cell. But because I don't have TensorFlow 2.0 by default, I'm going to have to rerun this cell here. So we run this, TensorFlow 2.x selected. Now, fingers crossed, if we have a GPU available, meaning super fast numerical computing, this little output message should change because this little piece of code is going to check to see if a GPU is available, which it looks like it is. Let's run this. Oh, yes. Woohoo! So now we have a GPU available, we have TensorFlow available, and we have TensorFlow Hub. Let's go have a look at our keynote where we're up to. We've done this. This is what we've done, except we've built it all up in Colab. So now we're ready to actually go to our workflow. I should have put step 0 on here as get our workspace ready, but this is really exciting. We can now get our data ready by turning it into tensors. So come back to our notebook. Make sure if you run this cell, you've got access to a GPU because the code we run later on will utilize a GPU. And make sure your TensorFlow version is higher than 2.x and your hub version, it doesn't really matter, but if it's 0.7 or above, that's a good thing. So I'll see you in the next video. Let's start figuring out how to get our data ready. Welcome back. So in the last video, we made sure that our Colab notebook runtime, or the machine that lives on Google's cloud server that our notebook is being run on, is using a GPU to power its computing. Now, I just want to show you something pretty cool about Colab as well. Because these notebooks are shareable, you can run them almost instantaneously. So this is optional video. If you want to just go back into getting our data ready, go skip this one and go into the next video. Just wanted to show you an example of a shareable Google Colab notebook, as well as how much a GPU actually speeds up compute. So if we go to a new tab, colabresearch.google.com, if we were to cancel out of this, the homepage of Google Colab is actually a notebook in itself. So that's the amazing thing. You can copy that to your Google Drive, or we can connect this to a runtime. And now a little bit of extra curriculum would be to go through this notebook here and just get familiar with Google Colab. Like there's a lot here, but you just saw that I connected that to a runtime and I can immediately start running code in this notebook. How beautiful is that? So if we go here, this is going to import NumPy, matplotlib, import pyplot as PLT. No setup. I just connected this to a runtime. That is amazing. And now there's a little section in here. If we go GPUs and TPUs, TensorFlow with GPUs. So this is what we just did in the last video. In our runtime, we're using a GPU. You can see that if I move the mouse, it's going to go away. We're using a GPU on this Dog Vision notebook. But if we click here, this little guide, this is going to take us to this website here. I'll attach both of these, by the way, to the resources section. Again, we just connect our runtime up here. This is going to give us a little insight into how fast TensorFlow is with a GPU and without a GPU. So if we go here, run this cell, it's going to make sure we're using TensorFlow 2 point something. And this is just a line of code to make sure. It's very similar. Oh, GPU not found. Why is this? Let's make sure it is. Change runtime type. It may be because I'm using a GPU in Dog Vision. You may be limited to only one. But let's see. Connecting. How beautiful is that? So if we run this, it says that we've got a GPU. Beautiful. So it's found a GPU at device GPU 0. So if we go here, this is observed speed up on GPU relative to CPU. I'm going to close this table of contents. We don't need that. So we've got a couple of functions here. What this is basically saying is run some code on the CPU and run the same code on the GPU. So there you go, with TF device GPU, CPU up there. So let's see. Shift and enter, run this. Just going to run some sort of loop a number of times. Shouldn't take too long. Convolve. Oh, there we go. Just going to convolve a filter over some random images. So it's processing images. That's exactly what we want to do, right? Look at that. Time to convolve 32 by 7 by 7 by 3 filter over. So this is just basically process some images of this over 100 or so images 10 times. The CPU took 3.4 seconds. The GPU took 0.1 seconds, or just over 0.1 seconds. So 30 times faster. Isn't that beautiful? First of all, the fact how instantly we can connect to using such fast computing in Google Colab. And second of all, if we use a GPU, we get a speed up of 30x. I just think that's amazing. And now, again, remember, any of these tutorials in Google Colab, if in doubt, run the code. Connect to a runtime and try it out. Run it for yourself. That's the motto, right? If in doubt, run the code. But again, this was just an optional video just to show you the power of Google Colab and the power of a GPU. Now, we know that what a GPU can do. Let's get back into our dog vision notebook and use one. All right, so we've seen this little, well, actually, you might not have seen this before, but I thought I'd make a quick video on what to do if you get this runtime disconnected message right down at the end of the notebook. So we've just saved and loaded a model, so a pre-saved model and a loaded model. But now, since our runtime is disconnected in Google Colab, we're going to have to reconnect and then rerun some of the variables we've run up the top to get access to them. So let me just show you what to do. So if I reconnect, we're going to have to wait for this to load up. Shouldn't take too long. And as you can see next, we're pretty far on in the project because next step for us is training a model on the full data. But if we try to access the full data, as you'll see in a second, initializing, mounting Google Drive, getting our data back, we're connected again. So before we saved our images in X, or if you're watching this before we get to this actual part, just know that our data is in X and our labels are in Y. But right now they're not defined. So because our runtime disconnected, it means we're going to have to go right back up to the top of the notebook. This is a beautiful thing about Google Colab is you can go right up the top. And we're going to have to rerun these. So we're going to have to re-import TensorFlow 2. We're going to have to re-import TensorFlow and TensorFlow Hub. There we go. We're going to have to get back our labels CSV. So just all of the variables that we've had later on in the notebook, we're going to have to rerun them. We don't have to look at this image. We've already done that. Again, if you're watching this in an earlier video, you'll see what happens as we get through the notebook. We do need file names. We do need to check this, make sure it's okay. We don't need to view one more image. So this is the kind of workflow you might have to do if you're working through your notebook and you take a break like I just have, and its real runtime is disconnected. Length labels. So we're just re-instantiating all the variables we're going to need later on. And as you get a bit more practice working with these kind of workflows, you might functionize what we're doing right now so that you can just run one cell and it sets up all of these, which is what we've tried to do later on. And you'll see pretty shortly that for things like loading our model, we can just run our load model function. Here's where we want, because we want to train a model on the full data. We need our X and Y variables, aka X is just file names to the training data and Y are labels. Remember, if you're watching this early on, don't worry, we're going to go through this. But I'm just showing you the kind of things you'll have to do if your runtime disconnects itself, which it will after an extended period of time away from Google Colab. Beautiful. There's a lot of stuff that we don't have to run. Mostly the functions is what we're after. So let's just keep going through this. I'm just rerunning all of these cells. We'll need to create training in. We don't need to look at data batches. So let's comment out this cell. We need to run this. Beautiful. We could go run all by just going runtime run all, but I just want to show you step by step what's happening. You'll get something like this. This usually fixes itself. If not, just click more info and have a read of what's actually going on. Early stopping callback, we do need that. Print GPU available, make sure it's available. We need the train model function. We actually don't need to train another model. So what we'll do is we'll comment out that. We don't need to look at TensorBoard just yet. And we don't need to make these predictions. We do need getPred label. We do need unbatchify. We do need plotpred. Do need plotpredconf. Don't need to rerun that. And we do need save model, load model. And now, as long as load model runs, we should be able to load a previously trained model. This one, loaded 1000 image model, should run. So if we go load in a model, now remember, this is just the kind of workflow you'll have to do if your runtime disconnects, which it will if you take a break. And you should be taking breaks. It's important. We just might speed the video up, make sure that everything's running, and we'll come back once this cell is loaded and run. Wonderful. So now we've loaded a model from our saved models directory. We come up in here, models. This video is from the future, remember? So we got dog vision, and then inside dog vision, every time you reconnect to a new runtime, it's going to take a while to load drive as things get stored in Google's machine. So we're loading it from models. And now we should be able to evaluate. And we should have X and Y, which is our full data set. Beautiful. Same results as the original model. And now X and Y are reinstantiated. So that's just a workflow you might have to take if your runtime disconnects and you're pretty far on in the notebook. Make sure you've got all the variables that you need loaded. I'm going to now train a model on the full data. But remember, if you're not up to this part just yet, don't worry too much. We're going to cover it in subsequent videos. I just thought I'd put this one in to show you what it looks like if you're pretty far on in the project and you have to restart your runtime. So I'll see you in the future videos. Now, this is exactly what I was talking about. If we go back to the keynote, things you might see in Colab, this is one of them. So what it means is that I took a little break just now, and if we come back to Colab, because of the limited amount of resources that Google is able to provide, if you leave your notebook in Colab for a long enough time, it will eventually disconnect from a runtime, which is, a runtime is again just a computer on Google's server that powers your notebook. So this is what you do if you have to take a break, and you should take a break every so often. You're not spending too much time sitting down. Go for a walk. Nature's beautiful, right? Well, that's what I just did. I just took my dogs for a walk. So if you do get this little pop-up, you're going to have to reconnect. But you'll see up here, the runtime is reconnecting. So it's initializing, mounting Google Drive, which is where our files are. Maybe it takes a little while to appear. There we go, Drive. We'll have Google Drive back. There's Dog Vision, our beautiful little project folder. Excellent, we can close this up, we don't need that. But what we're going to have to do is, oh, better tick off these, right? Pay attention to my own notes. I'll put a little green tick emoji. We've imported TensorFlow Hub, making sure we're using a GPU. Now, the beautiful thing is, the notebook itself will save the fact that we are using a GPU. So when it reloads, we won't have to change the hardware accelerator to GPU. It will automatically load it as a GPU. But we do have to rerun any cells that we may have ran before. So there we go. Check for GPU, import TensorFlow. Make sure we're using TensorFlow 2.x. And I'll delete this one. Wonderful. Okay, so now we've got our workspace ready. And you might be thinking, Daniel, that took a fairly long time to get set up. But as always, a person is only as good as the tool they use, right? Or as the tools they use. So that's why we spent a bit of time getting our Colab workspace ready, getting our new project folder together, getting our data there. So now, if we go back, what step are we up to? There should be a 0 here for getting our workspace ready. But now we're up to step 1, which is getting our data ready, aka turning it into tensors. Now, this is the premise of TensorFlow in itself. That's why it's called TensorFlow. The premise is to get your data into tensors, aka, remember, all machine learning models like to deal with numbers. So we have to get our data into tensors, which is just a fancy word for matrix, aka a NumPy array with some dimensions. But a tensor, the key thing here is that it can be run on a GPU. So if we go back here, TensorFlow is turn your data into tensors, and then it flows through a workflow like this. You get it? TensorFlow? Who knew? Doing a machine learning course and you get a comedy show for free. All right. So step 1, we're going to access the data. So right now it's over here in Drive, in the dog vision. So now we have to somehow get it from this folder into this code space. So let's do that. We'll get out of that. We'll make a little heading. Actually, we can go to here, getting our data ready, turning it into tensors. Remember, we're communicating with ourselves here. We go here with all machine learning models. Our data has to be in numerical format. So that's what we'll be doing first. Turning our images into tensors. Numerical representation. Okay. Now, this is a code cell, and in Colab, a special way to transform something into Markdown is to hold Command and double tap M. If you want to see a list of all shortcuts in Colab, hold Command MH. There we go. Have a look at that. Far out. There's a lot there. So this takes some practice, again, because some of the commands we've been using in Jupyter are slightly different. If you do need to look one up, have a look in here. Otherwise, I'll just kind of keep running with it. If I need to add a code cell, I can just press this little plus button here or up here. And the main one we'll be using is Shift and Enter, right? Just to run our code. Let's check out the labels. What does that look like? So if we come back, let's start by accessing our data and checking out the labels. So to do that, it's in a CSV format. So if we want to check it out, we might have to, or we will have to import pandas, because it's a lot easier to look at things that are CSV format using pandas. So check out the labels of our data. We're going to import pandas as PD, our favorite. Labels CSV equals. So what we're going to do is just pass in, maybe we could set up a little path, but we'll type it out to begin with. We could just copy this, copy path, but we're going to practice. What would that look like? Something like that. Let's practice typing it out. Remember, you don't need content. Drive, my drive, /dog vision. Oh yeah. This is what projects need, right? They need cool names. Labels.csv. All right. And we're going to can that. And then what we might check out is we'll get label CSV. We wanted to describe it. .describe would help if I could type. I be fourth time lucky. There we go. And print. We'll also get the head, so the first 5 rows. Let's check it out. Again, we'll remove this, more space. Wonderful. What do we have here? Count. 10,222 ID, breed, 10,222 unique values. So, okay. So there's 10,222 unique IDs and 120 unique breeds. And then this is what the ID column looks like. Again, it looks a bit different because we've printed it. So if we just did labels.csv.head, this is what you might be used to looking at, something like that. There we go. So we've got an ID column, which is the file names, I believe, of our images. So this is of train. and the breed associated with that ID. Now, a little tidbit here, if you do have a lot of files in one of your folders in Google Drive, it actually does take a fairly long time to load here. So rather than wait for that, let's just go back to Kaggle. We'll treat this as our way of looking at things. There we go. So if we go to label CSV, 10,222 unique values. Yes, that's correct here, unique. And then train, we've got unique ID. So does that look like what we've got in ID? Yes, it does. Wonderful. Okay, now what we might check out, we got 120 different breeds. So that means that there's 10,000 or so images. Hopefully, there's about 100 or so images per class. Well, actually, let's just figure that out. Let's figure out how many images there are per class first, and then we'll see why that's important. How many images are there of each breed? And we could probably do this pretty easily by going labels, CSV, breed. So I'm accessing the breed column. And then I'm going to go value counts. So count the values in this column. Actually, let's just see what that does. This is a dog breed, Scottish Deerhound, Maltese dog, Entel Butcher. Not even sure what that is. Shout out if your dog's on here. Eskimo dog. Yeah, that's really cool. Okay. And now let's visualize this. It's probably going to look a bit better if we visualize this. Fig size equals 2010. Whoa. See, the beauty of Colab is that we didn't even have to import matplotlib to see that. So my notebook's a bit zoomed in, but this is pretty cool. If we were to draw a line, so look, we've got dog breeds here, all of our 120 different dog breeds. And then this is the number of images that they have. So if we were to draw a line somewhere across here, we'd say about maybe 75 on average. We can figure that out pretty easily anyway. So labels, CSV, how do you find the mean of a column? Actually, we need to count them first, because otherwise they're just strings. Dot mean. Average. Median's probably a little bit more robust than the mean. So the middle number, 82. Okay, so we said 75, but that is a good thing. You could imagine, right? If you had, let's say, Scottish Deerhound, if we had 500 images of that, but this bad boy over here, what is this one? Eskimo dog. If we only had 3 images of Eskimo dog, we could imagine our machine learning model might do very well at figuring out what a Scottish Deerhound looks like because it has so many examples. But as for an Eskimo dog, if there's only 3 images, it's probably going to be a bit hard to figure out what it looks like. When you're asking yourself how many images should I have per class, Google recommends a bare minimum 10. Google minimum number of images per class. Preparing your training data. Here we go. So this is Google's AutoML, so which is their service for automatically building machine learning models. This is some extracurricular if you want to check this out. It's pretty cool. Preparing your data. There we go. For model training purposes, it is recommended you use about 100 annotations per label. So in our case, it would be great if you had 100 examples of each image class with at least 10. So 100 is great, but at least 10 is a good start. So if you wanted to build your own image classifier, if it's a binary classification, you'd want to be looking at minimum 10 images per class. So our data set at about 75 to 85 images per class is pretty well spread out. This is a good start. Okay, so I've done a little bit of exploration of the labels. Now, what we might do is start to get our image paths. So labels is pretty easy to deal with in a CSV, but all of our images, again, we can't see that, are in this format here. So we need a way to get them into our Colab notebook. Let's have a look at how to do that in the next video. Okay, so in the last video, we got in our labels.csv, which is now in the data frame label CSV, and it contains image IDs, which are file names, and their breed label. And then we checked out the distribution of our breed labels, and we figured out there's about 82 or so images per class. Now, it'd be good if we could view an image inside the notebook, because this is part of our exploratory data analysis, is checking out our data. Let's do that. Let's view an image. So one way to do that is using IPython. Remember, even though we're working in Google Colab, this is still under the hood a Jupyter Notebook. So we can go from ipython.display, import image. And then we can write image, and then we just pass it a file name. And a little trick here in Colab is before we had to press Shift and Tab in a Jupyter Notebook to find the doc string. In Colab, for me, it's Command space Shift. And then Siri comes up. So Command Shift space. There we go. On Windows, it might be Control instead of Command. So there we go. This is our doc string here. We need to pass it some sort of data. And if we want to see it, we need to pass it a file name. Let's grab one of these image IDs. So I'll just copy that. It should be, actually, let's have a look at a dingo. See, I'm from Australia, and we're pretty famous for a story called Dingo Took My Baby. I won't go into the details of that, but you can look it up. And then if we go here, so we go drive, we need to pass it a file name, my drive, file path, sorry. And then we got our dog vision folder, dog vision / it's going to be in the training folder, this, and we need to put on the end .jpeg, because if we come up to Kaggle, we can see that is actually what the file name is. That's the ID, but the full file name has the .jpg. Now let's close this bad boy and Shift and Enter. Oh, look at that. Cute little dingo, but apparently they can be savages at times. That's one way to view images in our notebook. So if we needed to explore what image we're working with while we're turning it into a tensor, we can use this little function here. Or I think there's another one with matplotlib. We can use imshow, but we'll have a look at that one later. Now we can view an image, and we've got their file IDs and their breeds. Let's get a list of all the file names, so we don't have to type out this every single time, because that would get annoying. So what we might do is write a little markdown cell here. So I'll press Command MM, change that into markdown, and go here, getting images and their labels. Let's get a list of all of our image file path names. Beautiful. And so how can we do this? So we might go here, create path names from image IDs. Now, we've just done one here. So this is a path name of this particular image. And we did it by stealing this value here from label CSV. We might bring label CSV down here just so we can have a gaze at it while we work with this. Label CSV dot head. There we go. So we might create a little variable to loop through this and create these long strings at the same time. So let's see if we can do that with a list comprehension. So file names equals, let's just go fname for fname to start with. We'll start small. In labels CSV ID, what does this return? Check the first 10. File names. Wonderful. So this is just a short little list comprehension. Basically, it's saying it's create a list of fname for fname, which is short for file name, in labels CSV.id column. So take this ID column, go through each one of them, and take the value and save it to the list. So that's what we've got there. Now we need to change it up to be a bit more like this, because these at the moment are just IDs. So what we'll do is drive my drive dog vision train. That's what we can do. Drive / my drive / dog vision. train, and then it's going to be plus fname. Oh no, end of string plus fname. What does that return? I said check the first 10 here, but I've lied. I didn't put the little slice. Okay, and now we just need to add, of course, the file extension, because otherwise it wouldn't work. These are JPEGs. .jpg. How does this look? Wonderful. Okay, so now we've got a list of all the file names from the ID column of label CSV. What we should do is compare them to the number of files in our training data directory. Why would we do this? Well, this is to make sure that we've got the same amount of file names as we do actual files in our training file. We downloaded this data from Kaggle. We uploaded it to Colab, or more specifically our Dog Vision folder, and then we unzipped it. So we want to make sure that we're working with the same amount of data. So let's do that. So we go here, check whether number of file names matches number of actual image files. Because otherwise, like if we just kept going now and we've worked out later on that, hey, we've got some issue with our data, then it's kind of going to undo a lot of the stuff that we've done. So that's a big point, is a lot of machine learning is just basically massaging your data into a form so that it works with machine learning, if that makes sense. So that's what we're doing now. We're just verifying that the data we've got is the right format, the right amount, and then we know once we run our machine learning models, they'll be all hunky-dory, or at least hunky-dory as possible. So we're going to import OS, and we can check the amount of files in a particular file by using list_dir. So len os list_dir. I'll just write the code, and then we'll explain it. Train, is that equal to len of file names? And if it is, print file names match actual amount of files. Proceed. It's like we're giving ourselves a little instruction here. Print file names do not match actual amount of files. Check the target directory. All right. So what this is going to do, if you do os list_dir, let's just see what this prints out. Code. Actually, I might only do the first 10 again, otherwise it'll be just spam. Name OS is not defined. Oh, that would make sense because I've got import OS there and not up here. Let's do it up here. So what this is going to do is tell Colab to, hey, go into Dog Vision train. Oh, I've just called it data. There's no file there. Stop that. By the way, if the executed code is not responding to interrupts. So if this comes up, it's because this cell is unable to stop. So these are the things you'll run into. And the reason why this is going in sort of an infinite loop is because I actually do have a folder called data, which is what this used to be. And within there is also a train folder. So it's looping through there. What I might do, can I can that? Boom, canned it. So let me just tell you what it does. OS list_dir is just going to go through a directory and then list all the files in that directory. So we're saying if the length of all the files in this drive, my drive, Dog Vision. Here's our other warning that's popped up. This is beautiful timing. So these are the actual things that you're going to run into. Go back to our keynote. Here we go. So this is a little error that you might experience if there's something going on with your Google Drive and the way that Colab is interacting with it. So the good thing is it usually fixes itself. And if you want to click this More Info tab, you'll get this little paragraph of text. So basically it's saying if you have a lot of files in Google Drive, in the top folder. So if we come back to Dog Vision, so in this folder here, if you have a lot of files there, Google Drive can time out, as well as if you have a lot of files within a particular folder, it can also time out. So that's very handy that we saw that in real time, because I don't want you to come across these warnings and not be sure of what to do. But if in doubt, remember, you can always just search this, ask a question. I'm sure someone will be able to help you out. If not, I'll help you out. Click the links. There's a bunch of things you can try out. Let's just run the code. We've spoken about it for too long. File names match actual amount of files. Proceed. Now, I will let you test this one out yourself. We're going to follow the orders of this code here and proceed. Okay, so everything's working. We have all the file names in a list, and we have the same amount of file names as we have actual images. Let's do one more check to make sure that we're visualizing directly from a file path. So we can go here, one more check. Remember, we want to make sure our data is in the right format. Let's go the 9,000th image, or 9,000th index. Good Lord. I wonder what type of dog that is. What an absolute beast. We can find out probably. Let's go here. Labels, CSV, ID, 9,000. Oh, no, we want breed. That thing looks savage. Look at the size of that chain. Tibetan Mastiff. That even sounds like a tough dog. I want one of them. That's a beast. That's like a dog Hercules would have. Okay. Now we've got all of our file names that are correct. What we're going to have to do, so we've got the file names. Now we need to work with our labels. We need to get our labels in a format that we can use. So let's do that in the next video. Alrighty. So now we've got all of our training image file names. Remember, these are just file names at the moment, or file paths, probably the better way to do it. I've called this file name, so we'll just leave that there. So these are file paths to our training images, which means later on we'll have a way to access them. So it's important to note here that these are just strings. They're not the actual images just yet. We'll do that in a second. But what we're doing now is we need to get our labels ready. So these are our labels. We've just dealt with the file IDs and turned them into file paths. But let's now get our labels. So remember, the premise of machine learning is to turn our data into numbers. More specifically, when we're working with TensorFlow, it's to turn it into tensors. That's what we're moving towards in this little subsection at the moment. We'll write a little bit of text here. Since we've now got our training image file paths in a list, let's prepare our labels. Okay, we've got all our labels in label CSV. Let's just have a look at them actually. Let's go labels. Let's just create a variable called labels CSV breed. Keep it simple, you know. What does this come out as? Okay, so that's D-type object. Remember, we have to start turning these into numbers. So we might turn them into a NumPy array. So import NumPy as... Now I wonder if I could just do this. Otherwise, I know another way to do it. And what if we go labels? Wonderful. How many are in there? Len labels. 10,222, which is amazing. The other way I was going to do it is if we comment out this. I'm doing command /. That's how you can comment out a whole line. And then we go to NumPy. Nice simple method in pandas. Same thing. Does same thing as above. Little trick there. Let's do the same thing as before. Compare the amount of labels to the number of file names. If we come back to here, after we've downloaded this and unzipped it into our Colab notebook, what we're doing here is by comparing the number of labels to the number of file names, checking for missing data. So if you remember back in the previous projects with structured data, there were some cells in the data frame that were missing. But checking it with unstructured data, if there's missing data, is a bit harder. So this is kind of the workaround we're doing. Check if number of labels matches the number of file names. And we're just going to do the exact same as before. So if len labels, so the length of labels, what we just did there, equals len file names, because what we're eventually going to have to do is pair up these labels with these file names, like what we've just done here. So index 9000 is Tibetan Mastiff, and its file name 9000 is this absolute lion of a dog. So let's go here, we'll print out a little confirmation for ourselves. Number of labels matches number of file names. Beautiful. Else print number of labels does not match number of file names. Check data directories. Fingers crossed. Beautiful. That's what we're after. Number of labels matches number of file names. Okay. Now, finally, since a machine, well, not really finally, we've still got a lot to go with this project. Since a machine learning model can't take strings as input, this is what labels currently is, right? It's an array of strings. What we have to do is convert it into numbers. How might we do this? Well, to begin, let's find a list of all the unique dog breeds. So there's 10,222 in here, but how would we find the unique labels? So let's do this. Find the unique label values. So I want you to have a little think about this. If you have a NumPy array, I've given you a little hint. How might you find the unique values in a given array using NumPy? Did you have a little think? You could even look it up. There's a good Google search for that. So NP unique is how we find the unique elements of an array. And now this is pretty cool with Colab, right? It just pops up this doc string without me even doing anything. So we want to find the unique labels. Let's find that. Unique breeds. Let's have a look at that. Awesome. So there's a whole bunch of different dog breeds. So let's have a look at them. Brittany Spaniel. I never even heard of that. Chihuahua. Gordon Setter. Great Dane. Yeah, there's a beast. Okay. Getting distracted by dogs. And so this should be 120. Wonderful. So that is because we have 120 breeds of dogs. We're lining up here, right? We're getting our data ready. We're getting it prepared to get into tensors. We've only got two arrays of strings. How might we turn these into numbers? Why don't we turn it into an array of booleans? Let me give you an example rather than talk about it. So turn a single label into an array of booleans. So print label 0. We'll just use label 0 as an example. So label 0. Now we're going to use the comparison operator to compare the first label to unique breeds. And what this should return is an array of true and false values where everywhere in unique breeds, label 0 doesn't equal, it should be false, but the only location where it does equal should be true. There we go. Let's have a look at these. So it's a Boston Bull, but then if we have a look at unique breeds, so we can see true is here. So what's that, about 12 in? So if we go through here, count them up. If you counted them up, you'd find Boston Bull. There we go, true. That's what we're after. Let's do that for every single label. So turn every label into a Boolean array. If you're looking at this and this is just all trues and falses, you're probably wondering how is this going to be converted to numbers, but we'll see in a second. There's a special thing with NumPy arrays and Boolean values. So let's go Boolean labels equals label. We'll do another list comprehension here. So label equals unique breeds for label in labels. Whew. Let's see what the code says first, then we'll talk through it. If in doubt, run the code. Wonderful. And Boolean labels should be 10,000 long, or 10,222, whatever it was. Wonderful. So that means we've turned every single label into a Boolean label. Now, what is this little list comprehension doing? All it's doing is a scaled up version of what we've got here. So it's saying, do this little one-off example for every label in labels. And if we remember, then labels is 10,222 because we have 10,222 labels. So it's done it for every single label. You might be thinking again, why are we turning them into true and false? Well, how we can convert these Boolean arrays into numbers. More specifically, one-hot encoded numbers. So, if in doubt, run the code. Let's check out the code, then we'll talk it through. So, example, turning Boolean array into integers. Print label 0, we'll get the first one. So this is the original label, straight from the data frame, straight from label CSV. Print np where unique breeds equals labels 0. Print. So actually, we should probably tell, this is the index where label occurs. And then we're going to go print Boolean labels 0.argmax. So this is index where label occurs in Boolean array. And then we're going to go print Boolean labels as type int. So there will be a 1, or there should be a 1 where the sample label occurs. Whew, that's a big cell. But we're going to check it out. Look at that. So the original label is Boston Bull, and it appears at the 19th index, which is the same in our Boolean labels 0th index, so it appears at 19. And if we were to count this, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 is where 1 occurs. So now, every single label in Boolean labels is actually in this type of format. So there's a 1 where the actual label occurs. So if we did the same thing for, let's go 2, and then print labels 2, is Pekingese occurs right down here, and 0 for everything else. Wonderful. So now we've got our labels in a numeric format, and our image file paths are easily accessible because remember we've got file names. These are our image paths. They aren't numeric yet, but we can do that later on using TensorFlow. So now we've got our data in an accessible format. Let's create some training and validation sets, because if we come to our files, we notice when we download it from Kaggle, we only have a train and test set. To do our experiments, we want to split our data into training and validation. So that's what we'll do in the next video. Welcome back. So in the last few videos, we've been spending a fair bit of effort getting our data into an accessible format. Now we've got that. So we've got, let's just quickly have a look. We've got Boolean labels, which is our labels in numerical format. We'll have a look at the first 2 so it doesn't take up too much room. There we go there, true and false. We can access those as 0s and 1s really easily. And the same goes for our file paths. So these are our training images here. And we left off discussing how Kaggle doesn't provide us a validation set. So creating our own validation set. And so since the data set from Kaggle doesn't come with a validation set, we're going to create our own. And remember from way back in Machine Learning 101, the most important concept in machine learning is the three sets, aka the training set, the validation set, and the test set. So right now, we've got the training set and a test set. But we'd like this validation set, which is aka the practice exam. So to reiterate, we'll train our machine learning model on the training set. We'll evaluate it on a validation set to see if our experiments that we've been doing on the training set are going all right. And then finally, the final exam is our test set. So we'd like this little intermediate set to validate our initial experiment. So that's why we're going to make a validation set. And now to do so, what could we use? What have we used in the past? I want you to think about this. It was in the scikit-learn section. If you said train test split, you'd be correct. Now, it can be a bit confusing because it says train test split, but really the functionality of the function is just splitting data into two different sets, one set of certain size and another set of another size. Let's set that up. But first, what we might do is set up X and Y variables. Now, the reason we do this is because having to remember Boolean labels and file names is a bit tedious. So what we might just do is create X, which is our standard variable for your data, and Y, which is usually the standard variable for your label. So we're just going to make copies of those. Beautiful. And now, since we're working with 10,000 plus images, 10,222 to be exact, it's a good idea to start working with a portion of them first to make sure things are working before we go and train a machine learning model on all of them. This is a thing to note for your own projects, is that when you're doing experiments, remember, what's our goal? It's to minimize the time between experiments so we can figure out what works and what doesn't. And if we're using 10,000 examples every single time, that's going to take a while. And if you've never trained a machine learning model or a deep learning model on 10,000 plus images, so you don't have a perspective of how long that takes, you can take my word for it that it would take a long time. So we'll probably reduce it down and start with about 1,000 images to begin with, and then increase it as we need. So let's write a little note for ourselves. We're going to start off experimenting 1,000 images and increase as needed. Now this goes for not just images, but for all kind of machine learning projects. And we've seen this in the past using subsamples of our data. If you're working on a text classification and you had 100,000 emails and you wanted to classify whether they were spam or not spam, you might only start with 5,000 and then build up from there. So let's set a little parameter. So set number of images to use for experimenting. Now I want to show you something really cool within Colab. So we'll create a little parameter here. And now it's in capitals because a convention you might see here and there with deep learning projects is that hyperparameters, so things that you can set as a user, are often set in capitals. That's where you might see these variables that are in full capitals. So let's go 1,000. And then in Colab, it has this little cool tool that you can, it's like a magic function at param. And now I'm still working these out. So maybe you can leave a little suggestion on where I can find out how to make more of these if you figure it out, because I only know a couple. Now watch this. So what we've done is we've just gone, hey, this is a parameter that we can set, create a type slider. The minimum is 1,000, max is 10,000, and the step is 1,000. Num images has now just appeared. Look, if we go like this, oh yeah, 5,000, 5,000. 8,000, 8,000. Oh, I could play around with that all day. That's something that Colab has over Jupyter, aside from being backed by a GPU for free. All right, so now we've got a little parameter. We've got X and Y. Let's use scikit-learn's train test split. So let's split our data into train and validation. From model selection, import train test split. Now again, this is called train test split, but the basic functionality of this function is to split. You could do this manually by using indexing, but we'll just use a function to help us out. Is just to split data into two different sets, into training and validation of total size num images, which is this variable we've set up here. Run that cell. Xtrain, xval this time, not xtest, ytrain, yval equals train test split x up to num images. So it's only going to take the first 1,000 file names, because remember, x is just our file names. We haven't imported our images just yet because it's a lot faster to work with just file names. And y is our labels in Boolean form. Test size, again, this is just validation size, will be 20%. And then the random state is kind of like setting random seed. Well, it is like setting random seed to 42. So random state equals 42 is the same as going np random seed 42. And if you're not sure what np random seed does, there's a video on that. Otherwise, you might want to just quickly Google what does np random seed do. So if we go len xtrain, just to check all the lengths of our data are correct, because you wouldn't believe the amount of times I've been burned because my data was the wrong shape. You will spend hours battling to get your data into the right shape. Trust me. I've been there. All right, wonderful. So we've got 1,000 samples and we've got a 20% test size. So that means there's going to be 800 samples in the training split and 200 samples in the validation split. So let's just have a quick look. Let's have a gaze at the training data. So xtrain, just to verify that we're still on this earth, we're still working with the right stuff. Actually, that's a bit too many. I got to remember that these are full-blown Boolean labels, so there's a lot there. So train, we've got file paths, correct, that is what we want, and training for labels, we have Boolean labels. That is what we are after. All right, so now that we have our data into a training and a validation set, a small subset, mind you, because remember, our goal to begin with is to minimize time between experiments. What we can probably finally do is turn our images, or at least create some functionality to turn our images and labels into tensors. Let's do that in the next video. Alrighty, so now we've got our training split and validation split. Our X values are the file paths to our images, and our Y values, the labels, are Boolean NumPy representations of the labels. And so what we have to do now is, since our labels are already in a numeric format, we have to convert our images into numbers, or at least create a function to do so for us. So let's create a little heading for that. We'll make it pre-processing images, turning images into tensors. So we're kind of officially getting started on this step here. And now when I say turning images into tensors, this is a common theme you'll have no matter what kind of data you're working on. So even if it's not images, if it's something like an audio file or it's a text passage, you're still going to have to turn it into tensors if you're working with TensorFlow. And remember, tensors are a numerical representation kind of like a matrix. All right, so what's one way we could do this? Again, rather than pre-processing our images in the notebook, we might pre-process them only when we need to, because manipulating file paths is a lot easier than manipulating an image because it's working with less data. So because we've already got the file paths, I'm going to keep this theme for the rest of this project, and I'm saying might do, we're going to do this. We're going to start developing out some functionality for steps in the project. And what I mean by that is creating functions rather than just writing one line of code and then running the cell. This cell won't run because there's nothing there. In the beginning, when I first started out, that's what I would do. I would just run countless lines of code in countless cells and then keep running it. And then eventually, even if I was way down below in another part of the notebook, I would have to rewrite the same code I'd already written somewhere up here. So that's why we're going to start creating functions so that we can write code once. It might take a little bit of time to begin with, but we can reuse those functions later on. And that's what I want you to start thinking about in your workflows. If you're thinking, hey, I'm going to be pre-processing some data here, maybe I might need that functionality later. So I'll turn it into a function rather than just a one-off cell. So let's do that. To pre-process our images into tensors, we're going to write a function which does a few things. Now, this pre-processing function will be specific to images, but the concept remains the same. Whatever data you're working with, you're probably going to have to turn it into some form of tensor. So we want to take an image file path as input. That's what we've got so far. We've got image file paths. We want to use TensorFlow to read the file and save it to a variable. We'll probably call that variable image, nice and simple. 3, we want to turn our image, so the image variable, which will be a JPEG because that's the type of image file that we're dealing with, into tensors. 4, what should we do next? We need to resize the image. So because all of our images are different sizes, it's standard practice to usually resize all of your images, image classification or some kind of deep learning pipeline with images, into a standardized size. So we'll resize the image to be a shape of 224. Now, I want you to have a think about it without even having hands-on experience with reshaping an image. Why might it be important to have it? Now, this size can be arbitrary, but why might it be important to have images of a similar size when you're working with them? Finally, return the modified image. Now, we've got 5 steps there for the function. You might be thinking, wow, how can I do that? Well, I want you to have a look at a resource here. So TensorFlow data loading. Here we go. So I'll leave this as an aside that you can start to read of how to load data into TensorFlow. So this is a really good section to check out. So TensorFlow guide data, I'll leave that in the resources section as an attachment. If you want to check it out, I just spend 10 minutes reading through here. Maybe you could spend 10 minutes over the next couple of days. Even if you don't understand it, just starting to get some of the concepts together. And now, as for tutorials, there should be another one here. I think load and pre-process data. So this is another valuable one. We come here. So this is what we're going to be doing, loading images. My problem is trying to load images, and I want to know how to turn them into tensors. So I go to tutorials, I look up load data, and I'd look up how to load images. And then you could read through here. So I'll make sure that I link these 2 resources, and after you finish this video, I want you to read through them for about 10 minutes each. So let's go back and let's build this function out here. But before we do, I just want to give you a demonstration of what an image actually looks like if we were to read it in, and what a tensor looks like. So let's convert an image to a NumPy array right here. Before we do, let's see what importing an image looks like. So convert to NumPy array. Remember how I said tensors are very similar to multi-dimensional NumPy arrays or matrices? That's what we're going to see now. So we're importing just a matplotlib function imread, which stands for image read. I'm going to save image to imread. Let's get file names 42. Remember, file names is just a list of file paths to our training images, which is up here. Dog vision, training images. And then we want to check image.shape. Okay, so this is our image here. This is height, width. Actually, I always get confused, but that's why we kind of reshape them to be like a square image so that height and width doesn't really matter. I believe it's height, width, color channel. And what I mean by color channel is red, green, and blue pixels. So if we go here, what is a color channel? Channel RGB color sample. So this is what an image is made up of. Red, green, and blue colors. I'll let you dive a little bit more into that yourself, but you're just going to have to trust me that each pixel in an image here is some combination of red, green, and blue values. And they range from 0 to 255. So if we have a look at our image, which is a NumPy array, it should be, there we go, values between 0 and 255. So if we go image.max, maybe this will tell us, 255, and image.min, 0. There we go. So red, green, and blue pixel values between 0 and 255. That is literally what our image is. Now, it's in a NumPy array at the moment. And remember how I said tensors are very similar to NumPy arrays? So let's turn this into a tensor. And we can do that. You can turn almost anything into a tensor by using tf constant. Now, if we read the docstring, creates a constant tensor from a tensor-like object. Beautiful. You can read a little bit more into that, but remember our motto, if in doubt, run the code. So that's what we're going to practice. Let's see what this does. We've got the exact same values. Actually, let's demonstrate this. We want image and maybe only up to 2. Same with tf constant. So the only difference here is that now we've got it in a tensor of shape 2, 353, and now it's shape 2, 353. We've indexed it to only show 2. But if you see, this is an array, NumPy, and this is a tensor. The only difference here is that this tensor is in TensorFlow, and now it's able to run on a GPU, so a lot faster compute. So our GPU will be able to find patterns in these numbers a lot faster than what our CPU, which is on my current machine, my MacBook Pro, will be able to find patterns in these. Let's go here, turn image into a tensor. So now we've seen a little bit of the basics behind what an image is composed of, what kind of data, pixel values, red, green, or blue between 0 and 255. We've seen what an image looks like in a NumPy array, and we've seen what an image looks like in a tensor. Let's finally get to our function, which has to do these 5 steps. So what we might do to save this video from getting too long, I know I said we were going to check out write a function, but I think it's good to build some intuition before we actually do write this function. We'll build this function in the next video. So in the meantime, try import one of your own images here. You can choose any file name number and then just have a play around with the different values and try turning it into a tensor. Now we've seen what an image looks like in tensor form. Let's build this little function that's going to do these steps here. So what we might do is just copy them so we can see them down below. I'm going to just write a little cell here. Now we've seen what an image looks like as a tensor. Let's make a function to pre-process them. Alrighty. And so what we might do is define a variable here, image size 224. You might be wondering, like I always do when I see things like this that aren't explained. What is 224? Where did I get that? Well, we're going to see that in a later video when we pick out a machine learning model that we can use. And so a lot of machine learning is lining up the size of your inputs or the shape of your inputs, in our case images, with the model that you're using. Again, we'll cover this later on, but essentially we're making sure that our images that we feed into a machine learning model are of this shape, so 224 high, 224 wide, because that is what the machine learning model that we're going to use was trained on. Images in that same shape. Remember how it's important to feed data in the same format and shape to your machine learning model as it was trained on when you're trying to make predictions. But we'll see that in practice later on. But let's write this function. So create a function for pre-processing images. So I'm going to call this nice and simple, process image. It's going to take an image path as input. And a little docstring could be takes an image file path and turns the image into a tensor. Something simple like that. We could make it a little bit more intuitive later on, but to begin with, that's enough to explain it for ourselves. So we want to read in an image file, and to do that, we'll save it to a variable called image. And if we read through loading images, now you can do this for other types of data too, right? There's text data there, there's pandas data frame, numpy CSV. But reading through there, we see that we can go tf.io for input output, read file. There we go. What's this say? Reads and outputs the entire contents of the input file name. Well, that makes sense. Returns a tensor of type string. Beautiful. Let's do image path, but don't take my word for it. What we'll do is, and I want you to adopt this practice too. If you ever see a function that you're not entirely sure of what it does, rewrite it line by line. So let's check this out. We'll go tensor equals tf.io read file, and then we need an image path, so we'll do file names. I'm 26, so we'll get file names 26. And what's that look like? Oh, so it's shape of a string. And then a whole bunch of characters I don't understand. But that's an alright thing because the computer understands them better than I do. So what it's done is it just taken the file name and turned the contents into this long tensor. Wonderful. So the next step, use TensorFlow to read the file, save it to image. Yep. Turn our image, a JPEG, into tensors. Okay, so let's do that. Turn the JPEG image into numerical tensor with 3 color channels. Red, green, blue. And again, checking out the loading images documentation. So we're reusing this variable here. Now we're going to reset it to be tf.image.decode. See how we've got some options here? We've got PNG, which is the type of image file. We're going to use JPEG because our images are in JPEG. Image, and then we pass it the variable channels. The ATA channels indicates the desired number of color channels for the decoded image. In our case, we want 3 for red, green, and blue. Beautiful. Now, again, if we wanted to check out exactly what this is doing, let's take tensor and go tf.image.decode JPEG. We'll take tensor and then we'll go channels equals 3. Oh, look at that. You've got exactly the same sort of data as that we have up here. Wonderful. All right, now to save, in the interest of time, we're going to write a couple more lines in this function, but we won't go through these similar steps. That's what I want you to have some practice doing. If you do see a function and you're curious to what it does, try writing it out line by line and see what happens. So you're just going to have to trust me with what these lines do. So convert the color channel value. So this is called normalization. I'll write the code first and then tell you about it. From 0 to 255 to 0 to 1 values. So we want to go image equals tf.image convert image dtype image tf float 32. Now, what's the docstring say here? Convert image to dtype, scaling its values if needed. Images that are represented using floating point values are expected to have values in the range 0, 1. Wonderful. Now, you might be thinking, how do you know this, Daniel? How do you know that you have to convert it from 0 to 255 to between 0 and 1? Well, actually, I lied. I said we weren't going to look at that, but this is a good one to investigate. Tensor, just so you can see, we've got values there between 0 and 255, and now I'll run this. Oh, no, I don't actually want that. Messing myself up here. We'll rerun this. So I just want to demonstrate what this is doing. So image convert. So basically all it's doing is it converts our values, it scales them. Instead of being between 0 and 255, they now are between 0 and 1 with the same scale. Float 32. Oh. tf.float 32. Wonderful. So we've got the same shape, but now instead of being between 0 and 255, they're between 0 and 1. And now this type of process makes computing on these more efficient. That's the most you need to know. It's called normalization. And again, this is just straight from the loading images documentation. Now what do we have to do? Actually, I don't think we had a step here for that. We might have to put in for normalize our image, convert color channel values from 0 to 255 to 0 to 1. There you go, 5, 6. Okay. Now finally, we can resize the image. Now, by now, I believe you trust me in what this line is going to do, so we're not going to type it out. I'm going to leave that to you. 224, 224, so basically a square. Exactly a square, actually. Image.resize. Resizes images to size using the specified method, okay? And now we want to resize image, and the size is going to be height, width. Now you see why we define this here. Maybe that if we wrote this function a bit better, we could input image size as image size. That's probably a little bit better. Wonderful. And now you'll get this kind of practice as you start to write your own functions. The first time you write a function, it'll probably be pretty bad, pretty terrible. But then as you start to work out what your workflow is, you'll start to understand how to write a better function. Now, we can return the image. So what has this done? Has it done exactly what we just said? It takes an image path and an image size. We can define that here. It reads in the image file from the path name, beautiful. It turns the JPEG into numerical tensor, so we're just converting it to a tensor with 3 color channels, red, green, and blue, because that's the convention for most deep learning image models. They want red. I said read. Not that that's a bad thing. Reading is a great thing. We've then converted the color channels from 0 to 255 to 0 to 1 values, and we finally resized the image to our desired value. Now, we've written this in a function. So the beautiful thing is that we can use this later on. This is what I used to do, right? I used to run through these lines of code every time I wanted to process an image. Terrible workflow. So we can actually remove these. Remember, if you want to check out what the function is actually doing, break it down line by line. Takes an image path as input and then see what the rest of it does. Now I think that's enough for this video. We've got our function created, ready to pre-process some images. What we might do now is, again, if we were to read through the loading data in TensorFlow, I think it's this one, yeah. Back through here, there's a little section in here that TensorFlow likes to see things in the form of batches. So we'll figure what batches are in the next video. Alrighty, so now we've got a function to pre-process our images, aka turn them into tensors. We can now start to figure out what we need to do next. So we've got get data ready, turn it into tensors, pick a model. Well, we're not quite up to this. So if we come back, if we were to read a little bit more into loading images in TensorFlow, we'd figure out that TensorFlow likes to see things in the form of a data batch, aka a tensor containing an image example or a piece of data example. Remember, this is data agnostic. We're just using images as our practical example. So it likes it in the form of, okay, give me a piece of data and its label as a combined tensor so I can process them really fast. And if you're wondering what a batch is, well, it's also called a mini batch, which is aka a small portion of your data. Now, generally, if you're wondering what a good batch size is or how much is a small portion, 32 is generally the default batch size with most deep learning models. And I'll show you, this is how I figure out a lot of things. So we go Yarn LeCun batch size. And you might be wondering, who the hell is Yarn LeCun? What is batch size? All these things are new to me. Well, I want to show you a little trick. When you find or when you hear of someone who is, let's say, a figure in the field of machine learning or deep learning, a trick that I use to figure out what they think of a certain topic is I Google their name and I Google the concept I'm looking for. Another one is Jeremy Howard. So Yarn LeCun and Jeremy Howard, you could go Jeremy Howard batch size, Google that. I'm just telling you these two people off the top of my head. Yarn LeCun, I'll let you research him, but he is one of the founders of convolutional neural networks, which is kind of what we're going to use to process our images. But getting sidetracked here. If we Google Yarn LeCun batch size, and then we come to Twitter. Twitter's actually an amazing resource to figure things out. Look at this. Training with large mini batches is bad for your health. More importantly, it's bad for your test error. Friends don't let friends use mini batches larger than 32. Then we've got a paper here linked on different batch sizes. So I'll let you look into that. I'll link this tweet in the resources section so you can check out that paper. But this is what we're going to work towards. We're going to transform our data into batches of size 32 so they process really efficiently in TensorFlow. So let's make a little heading. Turning our data into batches. And these little tidbits, the one I just showed you, like searching someone's name, these kind of things I think are important, right? How would you know that if I didn't sort of tell you or you sort of didn't stumble across it? The only way I found that was by stumbling across, hey, there's all this great information that people are sharing. How do I find that every so often? And again, my way is not perfect, but it's helpful. I Google someone's name and a certain concept I want to find out about more. This is why it's important to share your work if you find something valuable. Okay, getting sidetracked once again, but why would we turn out something into batches? Well, let's say, why turn our data into batches? And if you're still confused on batches, we're just taking a small portion, 32 images, and calculating on those 32 images at one time. And then the next loop, the next training session, we calculate on the next 32. Because if we tried to calculate patterns in all 10,000 images, so here, let's say you're trying to process 10,000 plus images in one go, they all might not fit into memory. So what I mean by that is that a GPU has, although it's really fast at computing, it still has a limited amount of memory. And so my computer has 16 gigabytes of RAM. The GPU backing this might have 8 gigabytes of RAM. So if we have 10,000 plus images and we're trying to process the patterns on that in one go, that may be more than 8 gigabytes, which is going to slow down our training process. It's going to break everything. So that's why we do 32 at a time. So that's why we do about 32 images at a time. you can 32 images, batch size. That's right here. This is the batch size. You can manually adjust the batch size if need be. All right, so we spent enough time talking. Let's start writing some code. What do we need? So write it here. In order to use TensorFlow effectively, we need our data in the form of tensor tuples, which look like this. So image in the form of a tensor and label. So as pairs. So then we'd pass 32 of these at a time to our machine learning model, and it would figure out the patterns in this image that relate to this label. And then it would end up doing that in a sort of loop fashion until it gets through all 10,000 plus images. Whew. All right. Let's build some functionality, but first we need a way to get tuples. So we need, before we can turn them into batches of 32, we need to get a tuple that looks like this. So let's write a little function. So create a simple function to return a tuple of tensors. That rolls off the tongue nicely. So we want to go def get image label, because we've got a function here that's going to return our image. So all we want to do is just basically get the label associated to whatever path we pass this function. So we'll go here, image path, and now really you're going to laugh at me for how simple this function is, because all we're doing is passing it the image path, the actual label, and the image pre-processing function we just wrote. So process image path, and then we want to go return image label. Look at that. How basic is that? So takes an image file path name and the associated label, processes the image and returns a tuple of image label. The doc string is longer than the function. Beautiful. We didn't even need that line. We could have just done it all return here. Now let's just give a quick example there. Let's just see exactly what this would look like. Process image. We want file names. Let's get 42, our favorite number. And what is it? What's it called? Boolean labels. We could just use X and Y, couldn't we? That's probably a bit better. X, Y, 42. Demo of the above. Beautiful. So that's in a tuple. Our image is in a tensor because we pass it to process image, but our label is not yet in a tensor, but that's all right. We could turn it into a tensor by just going tf constant. There we go. So now we've got a tuple of an image and label pair in the form of tensors. Now we're making some good progress here in getting our data ready. Remember how I said a lot of machine learning is just pre-processing your data into a format that fits into a machine learning model? That's what we're doing here. And now, again, this process we're sort of taking, getting our data into the format of data label in a tuple of tensors, is agnostic to whatever data you're using. So if you're not using images, you're using something like text, this would be a very similar process, except the way you pre-process the text will be different to the image. You still have to get it into tensors. All right, so we've got a little function to get image and label pairs in the form of tuples. We'll write a function in the next video to turn our image and label pairs into batches. And there's a few little tidbits that we need to pay attention to depending on if our images are in a training batch, a validation batch, and a test batch. But we'll see that in the next video. Okay, great. Now we have a little helper function that not only returns us our images in the form of tensors, it processes the images for us, but it also returns the label so we can get it back in a tuple form. So let's utilize that to write another function that's going to turn our data, all of our data, because this only does one sample. We need a way to turn all of our data, so our X and Y, our data and labels, into batches of size 32. All right. Now we've got, let's write that down. Remember, we're trying to communicate to ourselves here in notebooks a way to turn our data into tuples of tensors. And we go here in the form image label. Let's make a function to turn all of our data X and Y into batches. All right, wonderful. Now again, if you're wondering where all of this came from, a great place for any kind of data loading is to read through the documentation. I know it can be a bit boring sometimes, but trust me, reading through, even if you don't understand the first time, I didn't understand the first time, read through it, try it out again, and see how you go. This is going to be a big dog of a function. Oh, that's fitting because we're working on dog vision, but it's going to save us a hell of a lot of time later on. So let's do it. So we need to define the batch size. So 32 is a good start. Remember, TensorFlow defaults to 32 a lot. So if you don't set it somewhere, it'll probably default to 32, but we're going to define it anyway. So let's create a function to turn data into batches. And now we're going to write through this function together. And it's going to do a few little things differently depending on if we want a training data batch, a validation data batch, or a test data batch. Because remember, these are our three sets. There. So these are our three sets. So we've got a training set. We're going to turn it into a training batch, a validation batch, and a test batch. All right. So we want def create data batches. We want it to take in an X and a Y. And actually, Y can be none. Now, I want you to think about why Y might be none, because Y is our labels. This will probably make sense in a little bit. But just have a think about why might we want to create a data batch with no labels. Valid data equals false and test data equals false. And we'll leave ourselves a little doc string here. I used to have a colleague called Ron, and he told me a technique called rubber ducking. He was a lot better coder than I was. And he said, if you're having trouble figuring out how to do something in code, write it out in language first, or say it to yourself in language, as if you're talking to a rubber duck. And rubber ducks don't understand English very well, so you have to make it very clear. That's a great tip from Ron. Thank you, Ron. So this function creates batches of data out of image X and label Y pairs. It shuffles the data if it's training data, so mixes the data around, because if there was some inherent order into the training file that we downloaded, probably not, because these look pretty jumbled up. We don't want our model to remember that order. We want it to be as adaptable as possible, no matter what order an image comes in. But, so if it's training data, shuffle, but doesn't shuffle if it's validation data. Now, I want you to have a think about why it might not shuffle if it's validation data. Don't worry, we'll cover that, but just have a think about it for the meantime. Also accepts test data as input. Now, here is why Y might be none, because test data doesn't have labels, of course. Now, what we want to do is build a function that kind of does the same thing, but has some if clauses or elif clauses if it's valid data or test data. So we know what we kind of want to do. And we've got some conditions here that if it's valid or test data. So let's start off with the test data because I think that's the least amount of things. So if the data is a test data set, we probably don't, I was about to write definitely have labels, or we know we don't have labels if it's a test data set. So we'll go if test data, print, let's give ourselves a little heads up. I love giving myself a little heads up of what's going on. Creating test data batches just to make sure that later on, hey, maybe we're making some data batches and we've accidentally passed a false parameter to test data and it ends up doing it differently for the test data. We don't want that. We want to know that it's making test batches. So data equals tf.data.dataset. So this is the module in TensorFlow data. We're making essentially a batch data set. And we're gonna, this is a little interesting one here from tensor slices. So it creates a data set, aka just a TensorFlow data set, whose elements are slices of the given tensors. So basically what this says is pass me some tensors and I'll create a data set out of that. A little confusing, I know, but this is just how it's done in TensorFlow. TF constant X. So basically what this says is I'm going to create a TensorFlow dataset from the tensor slices, X, and because we're passing X to TF constant, it turns X into a tensor. So this is only file paths, no labels. Okay, and now data batch, here's where we turn our TensorFlow dataset, because right now, this would turn all of X into a data set. We need to turn it into a batch size of 32. So equals data.map. We need to process the image. And we need to turn it into a batch size. Whoa, a lot of stuff going on here, Daniel. What's happening? Well, we've talked through the line above, but this one, all it's saying is basically take this data, which is a TensorFlow data set made of X, which is just file names in the form of tensors, and then map our process image function. See, this is why we made it into a function, so we can call it process image. It's going to go through all of these steps here on our file names. So it's going to import them, turn them into normalized tensors, and then turn it into a batch of batch size. Let's go here. So TensorFlow data batch. This is the workflow I use whenever I'm looking up a function. So if we go batch, there we go, batch, combines consecutive elements of this data set into batches. There we go. So if we pass it a range of 8 and we want it to be a batch of 3, it's going to split 8 into 3 batches. So that's just exactly, why is this in a new tab? That's what it's going to do here, except ours is of size 32. Wonderful. So that's the test data. Now we want to do, if the data is a valid data set, we don't need to shuffle it. Now I want you to think about, again, why would we not need to shuffle it? It's okay if you're not entirely sure. I got caught out on this a lot of times too. So we'll print a little progress statement here. And then we'll do much the same as this. We could just copy that, but we're going to practice writing it out. TF data dataset from tensor slices. Now, this is where, because our validation set has labels, we're going to pass it a tuple of X and TF constant Y. So just turning our file names and labels into tensors. And we got here, file paths, labels. So now we have a TensorFlow dataset of image file paths and labels because it's a validation dataset. The validation dataset has labels. And we're going to turn it into a data batch equals data.map, just the exact same as above, process the image and turn it into a batch of batch size. Oh, getting trigger happy. Wonderful. And then return data batch. And finally, we want, if none of these work, well, if valid data is false and test data is also false, it's obviously going to be a training batch. So we're going to go create training data batches. Boom, boom, boom. And let's go. So if it is a training data set, we want to shuffle it. That's the only difference here. So we want to go turn file paths and labels into tensors. So just as we've done with the validation, we could just copy this. Now there's probably a more efficient way to write this function that does the same functionality, but I've tried to write it in a way that is fairly understandable as to what's going on. Constant X, and as I said that, I might have said that it's fairly understandable, but if you're coming across something like this for the first time, trust me, when I did, I was confused, but once I went through it step by step, remember our technique for breaking down a function, write it out line by line, and check out what it's doing at each line. So we want to shuffle the path names and labels before mapping. We'll go into this in a second. Before mapping, image processor function is faster than shuffling images. I'll just write the code so we can talk about it. But data shuffle buffer size. So buffer size just stands for how many variables do we want to shuffle, and we want to shuffle the whole lot. Whoa, a lot going on here. Well, all this is saying is, hey, take this data, which is a TensorFlow data set of the data, so the file names and the labels, and then shuffle it up. And we want to shuffle the number of examples. If we only shuffled 100, it would take the first 100 examples of X and Y and shuffle them. But no, we want to shuffle them all. And the reason being, you might see other tutorials shuffling later after we run the map function. Equals data map process image. So if you did shuffle after you've already processed the image, it takes a lot longer to shuffle a full image than it does just a file name. So as I said, remember, we're trying to minimize the time between experiments. So we want to try and get any speed ups that we can. I've just realized we've made a little mistake up here. In our validation data set, because we have images and labels, we need to map the function getImageLabel, which also processes our image. Whereas for our test data set, because we have no labels, we can run directly the processed image function. So let's replace this, getImageLabel, and it's going to be the same for our training data set. So getImageLabel, wonderful. And we might just write out what this is doing with a little comment. So create image label tuples. This also turns the image path into a pre-processed image. So if you can, shuffle your data when it's in its smallest format, aka, in our case, file names rather than full images. And now finally, we want to turn the training data into batches. So data batch equals data.batch batch size. And then we'll go out here, return data batch. Whew, that's a bit of a behemoth of a function, but as I said, this is going to save us a lot of time later on, and you'll see that. Remember, this is the kind of development work style I want you to start thinking about. Hey, am I going to reuse some functionality later on? Well, if I am, I'm going to write it into a function. And you probably already know that because you're a lot smarter developer than what I am. I used to just fluster around and just write things line by line. Now, let's test our function by creating training and validation data batches. So we'll go train data. We're going to use our big dog function just above. We're going to pass it xtrain for the training data and ytrain for the validation data. and that's all we need. And then for the val data, we could go create data batches, xval, yval, is it valid data, equals true. And now, fingers crossed, we should see our print progress messages. Oh, yes. That is amazing. Okay, now let's check out the different attributes of our data batches. So if we go train data, it's now in the format of a data batch, which is TensorFlow's preferred way of processing things. There we go. This is our training data, the first one here. What's it saying? So we've got shape none 224 2243. This is our image. None is for batch size. I know we've set it to 32, but it's going to stay as none because batch size, remember, is flexible. So this is just our images are now in batches of 32, and they've got a shape of 224 2243, height, width, color channels of type TF-float32. And we've got a tuple here of our label. So these are image label pairs in the form of tensors. And our labels also have a batch shape of none because batch size is flexible. And they have a dimension of 120, which is because if we go Y0, there's 120 different dog breeds. And then it's the same again for the validation data. Beautiful. So that was a pretty in-depth one. Once this video is over, which will be in a few seconds, I'd go back through and just read through what's going on in this function here. If you're not entirely sure, I'd look up loading and pre-processing data tutorial of images, have a read through that, and then the best way to learn is to really just write this out, break down the function, and try to run it line by line. That's how I break down things for myself. But the way our data is at the moment, it's still kind of hard to understand. If you're new to the concept of batches, it's probably a very difficult concept to grasp. It's perfectly okay not to know what's going on right now. So to help ourselves understand, rather than just having this gobbledygook being printed out when we're trying to check out what's in our data batches, let's write a function which is going to help us visualize what's going on. So that's what we'll do in the next video.